Hello there, and welcome to Science for Sleep, where curiosity slows down for the evening, where enormous questions drift gently through the dark, and where tonight we're going to spend some time near one of the most violent events in the entire universe. Not loud violence, though. Not explosions in the way movies like to imagine them. Black holes are stranger than that. Their collisions happen in silence. No fire, no shockwave roaring through space. Just darkness pulling on darkness until the fabric of reality itself begins to shake. Tonight's slow journey is about what really happens when two black holes collide. Now, that sentence alone sounds dramatic enough to belong on the cover of a science fiction novel. Two invisible monsters crashing together somewhere in deep space, while galaxies quietly spin around them completely unaware. Yet the remarkable thing is that this is not speculative anymore. Human beings have actually detected these collisions. We've measured them. We've listened to the ripples they create. And somehow, from our small planet orbiting an ordinary star, we learned how to hear the universe tremble. But before we drift toward merging black holes and warped space-time, let me ask you something gentle for the evening. Where are you listening from tonight? Maybe you're curled up in bed with the lights off and your phone balanced somewhere dangerously close to your face. Maybe there's rain tapping softly against the window. Perhaps you're listening during a late-night train ride, or while half asleep on a couch after promising yourself you'd only watch one more video. And what time is it where you are right now? Fitting, really, for a conversation about black holes and gravity and the strange flexibility of time itself. If you find this little corner of the universe relaxing or interesting, I'd be ever so grateful if you liked the video and subscribed. It helps this sleepy expedition continue drifting outward toward other curious minds who might need a quiet place to rest for a while. Now then, get comfortable. Let your thoughts loosen a little. There's no rush tonight. Black holes are patient things. Some spend billions of years slowly circling each other before finally meeting. Compared to them, even mountains are temporary. And in a way, that's part of what makes black holes so unsettling. Most things in the universe announce themselves. Stars shine, planets reflect light, nebulae glow softly in clouds of gas and dust. Even violent events like supernovae burst outward with extraordinary brightness. The cosmos is usually quite willing to show us what it's doing. Black holes refuse. A black hole is an object so dense that gravity becomes overwhelming. Once something crosses a boundary called the event horizon, it cannot escape. Not matter, not light, not information, at least as far as we currently understand. From the outside, a black hole looks almost like an absence, a missing piece of reality, a place where the universe stops sending updates. And yet these invisible objects can become heavier than entire clusters of stars compressed into a region smaller than a city. Which means something extraordinary happens when two of them begin to orbit one another. Imagine for a moment two perfectly invisible whirlpools in space, not empty holes floating around like cosmic vacuum cleaners, but regions where space-time itself has become deeply curved. Everything nearby bends toward them. Light changes direction around them. Time slows near them. Entire stars can be torn apart if they wander too close. Now imagine two of these objects trapped together by gravity. At first, they may be separated by enormous distances, millions or even billions of kilometers apart. From far away, the system might not look dramatic at all. In fact, if you could somehow watch it safely from a distance, the motion could appear strangely calm. Two dark bodies circling each other in silence. Slow, predictable, almost peaceful. But hidden underneath that calm movement is one of the most extreme processes in existence, because every orbit steals energy from the system. Very slowly the black holes spiral inward. This is one of the strangest things Einstein ever predicted. As massive objects accelerate through space-time, they produce ripples called gravitational waves. These waves spread outward at the speed of light, carrying energy away from the orbiting pair. So each time the black holes circle one another, they lose a tiny amount of orbital energy. The result is subtle at first. The orbit shrinks, then it shrinks again and again. Over millions of years, the two black holes draw closer and closer together like dancers slowly tightening a spiral. Except these dancers weigh more than stars and distort reality around themselves. Oddly enough, the final collision happens incredibly quickly. A process that may take billions of years eventually reaches a point where the last few moments unfold in seconds. Toward the end, the orbit becomes unbelievably fast. The black holes whip around each other dozens of times per second. Spacetime churns violently around them. Gravitational waves grow stronger and stronger. The entire structure of nearby reality begins shaking like water around a spinning drain. And then the black holes touch. Except, touch may not even be the right word. This is where ordinary language starts to fail us a little. Black holes do not have surfaces like planets or stars. There's no solid crust, no ocean, no atmosphere. The event horizon is not a physical shell you could stand on. It's more like a boundary in geometry, a region beyond which escape becomes impossible. So when black holes merge, it is really space-time itself rearranging. Two event horizons become one. Two regions of impossible gravity combine into a larger region of impossible gravity, and in that instant an astonishing amount of energy is released, not as light, not as sound, but as pure gravitational distortion. For a brief moment, the collision can release more power than all the stars in the observable universe combined. That statement sounds exaggerated. It sounds like the sort of sentence science communicators sneak into documentaries because it feels dramatic enough to keep viewers awake. But it's true. When the first black hole merger was detected in 2015, about 3 solar masses were converted directly into gravitational wave energy in a fraction of a second. 3 suns. Gone. Not destroyed exactly, but transformed into ripples in space-time itself, and those ripples travelled across the universe for more than 1 billion years before reaching Earth. Think about how strange that is. Long before human civilization existed, before the pyramids, before mammoths disappeared, before our species even learned agriculture, 2 black holes collided in a distant galaxy. The universe shivered. Tiny distortions spread outward through space for ages beyond comprehension. And eventually, in 2015, those ripples passed through Earth. They passed through your city, through oceans and mountains and buildings, through every person alive at the time. The distortion was unimaginably small, smaller than the width of a proton, yet scientists built instruments sensitive enough to detect it. And suddenly humanity had done something extraordinary. We had not simply seen the universe, we had heard it. That moment changed astronomy forever. Before gravitational wave detection, nearly everything we knew about space came through electromagnetic radiation. Visible light, radio waves, X-rays, infrared. We looked outward and interpreted brightness. But black holes are difficult to observe directly because they emit no light. Gravitational waves change the situation completely. Now, we could detect invisible events. We could measure collisions happening in total darkness. The universe gained a new sense. It's difficult to overstate how remarkable that is. Imagine spending your entire life only able to see, then suddenly discovering hearing. Entire categories of experience would appear overnight. Thunder, music, voices, wind through trees. That is roughly what gravitational wave astronomy has done for science. And yet black hole collisions remain deeply mysterious even now. One reason is that black holes challenge almost every instinct we have about reality. For example, what actually happens inside a black hole? Nobody knows. General relativity predicts something called a singularity, a point where density becomes infinite and the known laws of physics stop functioning properly. But most physicists suspect this description is incomplete. Infinity in equations often signals missing understanding rather than literal truth. Quantum mechanics complicates things further. Relativity describes gravity beautifully on large scales, while quantum theory describes the microscopic world with astonishing precision. But the two frameworks refuse to cooperate fully inside black holes, which means when black holes collide, we are observing environments where our understanding of physics becomes incomplete. That alone makes these mergers extraordinary. They are not merely violent cosmic events, they are laboratories for testing reality itself. And strangely, despite all this violence, the universe remains mostly quiet afterward. The final merged black hole settles down surprisingly quickly. Physicists call this phase the ring down, which sounds oddly cozy considering the circumstances. The newly formed black hole vibrates briefly, releasing the last irregularities in gravitational waves before stabilizing into a smooth spinning object. Then silence returns. No flames spread outward. No debris necessarily explodes across the galaxy. Just a larger black hole sitting in darkness. If you were watching safely from very far away, you might almost miss the significance of what happened. Two ancient objects met after billions of years spiraling together, released impossible amounts of energy, shook space-time across the cosmos, and then left behind only a slightly larger region of darkness. There is something oddly unsettling about that restraint. The universe often behaves this way. Its largest events are not always flashy, sometimes they are subtle. Gravity in particular tends to work patiently, quietly, relentlessly. Even now, somewhere in the observable universe, countless black holes are orbiting one another. Some formed from massive stars that died together long ago. Others may live near galactic centers, where giant black holes dominate entire stellar systems. Some pairs are probably still billions of years away from collision. Others may already be in their final minutes as you listen to this. And perhaps the strangest part is that black hole mergers are not rare accidents. They are a natural consequence of cosmic evolution. Stars are born, stars die. Gravity gathers remnants together. Galaxies merge. Black holes drift inward. Eventually darkness meets darkness. The universe appears surprisingly comfortable with this process. Human beings, meanwhile, remain wonderfully uncomfortable with it. Black holes frighten us because they represent limits. Limits of visibility, limits of escape, limits of understanding. We instinctively dislike things that refuse to reveal themselves. A mountain can be climbed, an ocean can be crossed, a storm can be observed. A black hole hides its interior permanently, and when two of them collide, they briefly expose the edges of physics itself. There is also something psychologically strange about objects that affect time. Near a black hole, time slows relative to distant observers. This is not metaphorical, it is measurable. A clock near a black hole genuinely runs differently from a clock farther away. So in a sense, black hole collisions are not only collisions of gravity, but collisions between different experiences of time itself. The deeper we study these systems, the stranger reality becomes, and perhaps that is why people find black holes so endlessly fascinating. They sit right at the border between science and imagination, real enough to measure, strange enough to feel almost mythological. Ancient cultures filled the darkness of space with monsters and gods, because the unknown naturally invites storytelling. Today we fill it with singularities and event horizons. The vocabulary changes, but the feeling remains surprisingly similar. We stare into darkness and wonder what rules apply there. Fortunately for us, the universe leaves clues, tiny ripples, faint signals, mathematical whispers arriving from impossible distances. Most objects in the universe are surprisingly understandable once you spend enough time with them. A planet is complicated, certainly, but you can still picture it. Oceans, mountains, storms, deserts, gravity pulling everything toward a center. Stars are more extreme, yet the basic idea still feels familiar. A giant sphere of hot gas producing light and heat through nuclear fusion. Even galaxies, despite their impossible scale, can still be imagined as enormous collections of stars slowly turning, through space like glowing cities seen from very far away. Black holes are different. The moment you try to picture one properly, your intuition starts slipping sideways. Part of the problem is the name itself. Black hole sounds deceptively simple, almost like a tunnel or a tear punched through the universe. Many people unconsciously imagine an actual hole floating in space, something like a cosmic drain with matter swirling into emptiness. That is not really what a black hole is. A black hole is not a hole in the ordinary sense at all. It is a place where matter has been compressed so intensely that gravity overwhelms every other force in nature. The object becomes so dense that escape becomes impossible once you cross a certain boundary. Light cannot leave. Information cannot leave. Space and time themselves become deeply distorted. And already, even that description begins causing difficulties, because black holes are not merely objects sitting inside space. In a meaningful sense, they reshape space itself. To understand this properly, we need to slow down a little and begin with gravity, because gravity is both the simplest and strangest force humans encounter every day. At first glance, gravity seems straightforward. You drop something, it falls. The Earth keeps the moon nearby. Planets orbit stars. Very practical, very dependable. Gravity feels almost boring compared to electricity or explosions or volcanoes. Yet gravity is secretly extraordinary. Every object with mass affects space around it. Einstein showed that gravity is not really an invisible force pulling objects together across distance the way Newton imagined. Instead, mass bends space-time itself. A common comparison is a heavy bowling ball placed on a stretched rubber sheet. The sheet curves downward around the ball, and smaller objects rolling nearby naturally move toward it, because the surface itself is distorted. That analogy is imperfect, but useful. The Earth bends space-time. The Sun bends it much more. A black hole bends it so severely that reality stops behaving in ways our brains evolved to understand. Oddly enough, black holes are not born exotic. Their origins begin with ordinary stars. Right now, the Sun is quietly converting hydrogen into helium deep inside its core through nuclear fusion. Every second, enormous amounts of energy push outward against gravity's inward pull. These two forces exist in balance. Gravity tries to compress the star. Fusion pushes outward. The result is stability. Stars live most of their lives maintaining this balance, but stars are temporary arrangements. Eventually they run out of fuel. For smaller stars, the ending is relatively gentle. They shed outer layers and slowly cool into white dwarfs. But massive stars live differently and die differently. The larger the star, the more violent gravity becomes when fusion finally weakens. Imagine a star dozens of times heavier than the Sun nearing the end of its life. For millions of years it burns heavier and heavier elements in its core. Hydrogen becomes helium. Helium becomes carbon. Carbon becomes oxygen and neon and silicon and eventually iron. And iron is the problem. Fusion involving iron does not release energy efficiently enough to support the star against gravity. The balance collapses. In a matter of seconds, the core implodes. This collapse happens so fast and violently that atoms themselves are crushed together. Electrons and protons combine into neutrons. The outer layers of the star rebound outward in a titanic supernova explosion, bright enough to outshine entire galaxies. What remains afterward depends on the original mass. Sometimes gravity is halted by neutron pressure, leaving behind a neutron star, an object so dense that a teaspoonful would weigh billions of tons. But if the core is massive enough, not even neutron pressure can resist collapse. Gravity wins completely, and this is where things become difficult to describe. The collapsing matter continues compressing inward, smaller, denser, more concentrated. According to general relativity, the process keeps going until all the mass collapses into a point of effectively infinite density called a singularity. Infinite density is one of those phrases physicists say very carefully because it tends to signal trouble inside equations. Nature rarely enjoys infinities. Most scientists, Suspect the singularity description means our understanding becomes incomplete at extremely small scales. Quantum effects probably become important there, but we still do not possess a full theory combining quantum mechanics and gravity successfully. So when people say black holes contain singularities, it is partly a mathematical statement, and partly an admission that physics reaches a foggy boundary. Still, whether or not literal infinities exist, the result outside the collapsing region is clear. Gravity becomes overwhelming. The escape velocity eventually exceeds the speed of light. And since nothing travels faster than light, escape becomes impossible. The boundary where this occurs is called the event horizon. This is the true defining feature of a black hole. Not the singularity, not the darkness, the event horizon. Cross that boundary, and every possible future path leads inward. This is an astonishing concept when you pause to think about it properly. Imagine standing near a steep valley. Normally you can climb back out if you have enough energy. But inside a black hole's event horizon, space-time itself becomes tilted inward so completely that moving away is no longer possible. Even light cannot find a route outward. That is why black holes appear black. Not because they absorb light like cosmic vacuum cleaners, but because beyond the event horizon, outgoing paths cease to exist. And here the universe becomes especially strange. If you watch someone fall toward a black hole from far away, relativity predicts something unexpected. Due to gravitational time dilation, the falling person would appear to slow down near the event horizon. Their movements would become sluggish. Light leaving them would redden and fade. To an outside observer, they would seem almost frozen near the horizon. But for the falling person themselves, time would feel normal. They would continue inward. This leads to one of the unsettling aspects of black holes. Different observers genuinely disagree about the sequence of events. Reality becomes perspective dependent in ways that feel deeply uncomfortable to human intuition. And black holes become even stranger when they rotate. Most black holes likely spin because the stars that created them were already rotating. Conservation of angular momentum causes the collapse to increase rotational speed enormously, much like a figure skater pulling their arms inward during a spin. A rotating black hole drags space-time around with it. Literally. This effect is called frame dragging. Nearby space itself becomes twisted by rotation. Around rapidly spinning black holes exists a region called the ergosphere, where space-time is dragged so intensely that remaining stationary becomes impossible. You're forced to move with the rotation, which sounds rather rude of the universe, honestly. Black holes also vary tremendously in size. Some stellar mass black holes contain perhaps 5 or 10 times the mass of the Sun compressed into a region only a few dozen kilometers wide. Others are supermassive black holes living at galactic centers. These monsters contain millions or billions of solar masses. At the center of the Milky Way sits Sagittarius, a star, a supermassive black hole weighing roughly 4 million suns. And despite all the terrifying descriptions, if you replace the Sun with a black hole of equal mass, Earth's orbit would remain nearly identical. We would continue circling normally. We would simply freeze to death because sunlight disappeared. That surprises many people, because black holes are often imagined as endlessly hungry cosmic predators, sucking everything inward. In reality, gravity depends on mass and distance. A black hole does not magically gain extra pulling power simply because matter is compressed. In fact, if the Sun somehow became a one solar mass black hole overnight, the main inconvenience would be the immediate extinction of nearly all life on Earth, which admittedly is a fairly significant inconvenience. Another misconception involves black holes wandering around devouring galaxies. Space is enormously empty. Objects rarely collide directly. Even near galactic centers, stars are usually separated by tremendous distances. Black holes influence nearby matter strongly, certainly, but they are not cosmic vacuum cleaners indiscriminately swallowing entire universes. Their true power lies in how extremely they warp nearby reality. and this warping produces extraordinary consequences. Matter falling toward black holes often forms accretion disks, enormous spiraling structures of superheated gas and plasma. Friction within these disks generates incredible temperatures. In fact, some regions near black holes become among the brightest places in the universe, precisely because matter heats so violently before crossing the event horizon. Ironically, black holes themselves are dark, but the material around them can shine with terrifying brilliance. Some supermassive black holes launch jets extending thousands of light years into space. Magnetic fields near the event horizon accelerate particles to nearly light speed, creating colossal beams detectable across galaxies. So black holes are not merely destroyers. They actively shape cosmic evolution. They influence star formation. They regulate galactic structure. They stir matter and energy across enormous distances. Without black holes, the universe might look profoundly different, and still, despite decades of study, fundamental mysteries remain unresolved. For example, what happens to information falling into a black hole? Quantum mechanics insists information cannot truly disappear. Yet classical black hole descriptions imply information becomes inaccessible forever beyond the event horizon. This conflict created the black hole information paradox, one of the most famous problems in modern theoretical physics. Stephen Hawking complicated matters further in the 1970s by showing black holes are not entirely black after all. Quantum effects near the event horizon allow black holes to emit tiny amounts of radiation now called Hawking radiation. Over immense periods of time, black holes may slowly evaporate. That idea alone feels almost absurd. The darkest objects in existence quietly glowing through quantum mechanics. The universe has a strange sense of humour sometimes, and perhaps the most remarkable thing about black holes is that they were once considered mathematical oddities unlikely to exist physically at all. Einstein himself disliked aspects of the solutions predicting them. For years, many scientists suspected nature would somehow prevent such objects from forming. Nature did not cooperate. Evidence accumulated steadily. Stars orbited invisible masses. X-rays poured from accretion disks. Galactic centers behaved strangely. Eventually, the evidence became overwhelming. Then, in 2019, humanity produced the first image of a black hole's shadow using the Event Horizon Telescope. Not the black hole itself, because no light escapes that. Instead, we saw the glowing material surrounding the darkness, outlining the event horizon against the brightness behind it. The image was blurry and orange and somehow profoundly emotional. After generations of equations and theories, humans had finally glimpsed the edge of one of nature's strangest creations. And yet even now, black holes remain elusive. You cannot touch one, you cannot see inside one, you cannot fully explain one using current physics. They exist partly as observations and partly as unanswered questions, which brings us naturally toward collisions. Because once black holes form, gravity continues working patiently. Stars orbit, galaxies merge, distances shrink. And sometimes two black holes become trapped together. Finding another black hole in the universe is not an easy thing. Space is unimaginably large, mostly empty, and often so spread out that even galaxies themselves are separated by millions of light years of darkness. If you shrank the Milky Way down to the size of a continent, individual stars would still be tiny and widely spaced. The cosmos is not crowded in the way science fiction sometimes likes to imagine. It is spacious to an almost uncomfortable degree, which makes black hole collisions seem improbable at first. After all, if black holes are relatively small, invisible and scattered through such enormous distances, how do two of them ever meet? Why don't they simply drift forever through the darkness, missing each other by colossal margins like ships crossing separate oceans? The answer begins with stars. Because black holes are born from stars and stars themselves are rarely solitary. This surprises many people. Our own sun lives alone, so it is tempting to imagine isolated stars scattered independently throughout space. But in reality, a large percentage of stars exist in binary systems, two stars orbiting each other around a shared centre of gravity. Some systems contain 3 stars, others even more. The universe, for whatever reason, seems quite fond of pairs. Imagine 2 enormous stars born together from the same collapsing cloud of gas and dust. From the beginning, gravity binds them into orbit. They circle one another slowly while spending millions of years burning through nuclear fuel. At first, the system may look beautiful rather than dangerous. 2 bright stars moving around each other against the dark background of space. Depending on their size and distance, they may exchange material through stellar winds. Their light may brighten and dim rhythmically as they orbit. Astronomers actually observe many such systems throughout the galaxy. But massive stars live fast. The larger a star becomes, the shorter its life tends to be. Very massive stars may survive only a few million years before collapsing, which sounds like a long time until you compare it to smaller stars like the Sun that can survive for billions upon billions of years. Eventually one star dies first. Its core collapses, a supernova erupts, and a black hole forms. Now, this is already a fairly chaotic moment for the binary system. Explosions can disrupt orbits. Material is blasted outward. Gravity changes suddenly. In many cases, the system breaks apart entirely, but sometimes it survives. The black hole remains gravitationally bound to the companion star. Then the second star eventually dies as well. Another collapse, another explosion, another black hole. And suddenly, after all that violence, the system contains 2 black holes orbiting each other in darkness where 2 stars once shone. This is probably one of the main ways stellar mass black hole binaries form, yet even then, the orbit may still be enormous. The pair could remain separated by millions of kilometres or more. Left alone, they might continue orbiting for unimaginable periods of time. So something else becomes important. Energy loss. This is where Einstein quietly enters the story again. According to general relativity, accelerating massive objects generate gravitational waves, tiny ripples spreading through space-time itself. The effect is usually far too weak to notice. Even Earth orbiting the Sun technically produces gravitational waves, but the energy involved is negligible on human scales. Black holes are different. When 2 black holes orbit each other, especially massive ones, they continuously radiate energy away through gravitational waves, and losing energy changes orbits. Picture a figure skater spinning with arms extended. As they pull inward, rotation speeds up. In a somewhat similar way, as black holes lose orbital energy, they spiral closer together and orbit faster. Very slowly at first. Painfully slowly, really. For millions or billions of years, the black holes continue circling each other, while gravitational waves quietly drain energy from the system. This gradual in-spiral is one of the most patient processes in the universe. Human civilization rises and falls during an almost imperceptible fraction of it. Entire species appear and vanish while the orbit shrinks only slightly. Continents drift. Stars move through galaxies. Meanwhile, the black holes continue circling. There is something strangely calming about that scale of slowness. The universe often behaves with extraordinary patience. Gravity especially never seems hurried. It simply continues pulling, orbit after orbit, century after century, until eventually even enormous distances begin collapsing inward. And sometimes the black holes do not begin life together at all. In dense regions like globular clusters or galactic centres, black holes can encounter one another dynamically. These environments are crowded by cosmic standards. Stars and stellar remnants move through relatively compact volumes, interacting gravitationally over long periods. Imagine a swarm of invisible heavy objects drifting through a stellar city. Occasionally 2 black holes pass near enough that gravity alters their trajectories. a third object may carry away excess energy, allowing the remaining pair to become gravitationally bound. Essentially, the universe occasionally arranges cosmic introductions through complicated gravitational encounters. One black hole loses enough energy to another interaction, and suddenly finds itself trapped in orbit with a partner. This is particularly important near supermassive black holes at galactic centers. Galaxies themselves frequently merge across cosmic history. When two galaxies collide, their stars usually pass by each other harmlessly, because the distances between stars are so enormous. Galactic collisions are more like giant overlapping clouds than car crashes, but their central black holes are another matter. As galaxies merge, gravity gradually drags the supermassive black holes toward the newly combined galactic center. There they may form binaries containing millions or billions of solar masses. These are among the largest black hole systems in existence, and their eventual mergers release unimaginable gravitational wave energy. In fact, future observatories may detect supermassive black hole collisions occurring across much of the observable universe. At the moment, however, there is still something called the final parsec problem, which sounds suspiciously like a science fiction pub name but is actually a serious astrophysical question. The issue involves understanding how supermassive black holes lose enough energy to close the final distance separating them. Early in the process, surrounding stars and gas help drain orbital energy efficiently, but eventually the black holes may clear out nearby material, potentially slowing further in spiral. Fortunately, current research suggests various mechanisms probably continue the process successfully. Additional stars drift inward, gas interactions occur, galactic asymmetries develop. The universe usually finds a way to continue collapsing things together. And honestly, gravity has a very strong track record in this department. Another fascinating aspect involves spin. Black holes are not merely masses moving through space. Many rotate rapidly, carrying angular momentum from the stars or previous mergers that formed them. This means when two black holes encounter each other, the orientation of their spins can influence the orbit dramatically. Some pairs spin in alignment, others tumble chaotically. The entire system can wobble and precess like an enormous distorted top spinning through curved space-time. Modern gravitational wave detectors are sensitive enough to infer some of these properties from merger signals, which is extraordinary when you think about it. Human beings have become capable of measuring the dance patterns of invisible objects colliding billions of light years away. There is also increasing evidence that some black holes may merge repeatedly. Imagine a dense stellar cluster where one merger produces a larger black hole. That remnant remains inside the cluster, later capturing another companion. Another merger occurs, then perhaps another. The black hole grows heavier each time like a cosmic nesting doll built from gravity and darkness. Some observed mergers already challenge our understanding of stellar evolution because the resulting black holes appear heavier than expected from ordinary star collapse alone. This suggests hierarchical mergers may indeed happen, black holes building larger black holes through generations of collisions. The universe, once again, turns out to be surprisingly recursive, and throughout all this, the collisions themselves remain almost entirely invisible until the final stages. No bright warning signals necessarily appear, no cosmic sirens announce what is coming. Two black holes can spend billions of years orbiting each other in perfect darkness, while the rest of the galaxy carries on normally around them. Planets orbit stars. Civilizations potentially rise somewhere nearby. Light crosses interstellar distances, and hidden within the dark, the orbit keeps shrinking. There is something eerie about processes unfolding on scales so detached from ordinary experience. Human beings naturally think in lifetimes, maybe generations if we are feeling ambitious. But black hole binaries operate on timescales so enormous they almost resist emotional understanding. Imagine beginning a journey before multicellular life exists on Earth and finishing it after mammals dominate continents. That is the kind of patience gravity works with. Yet the remarkable thing is how suddenly the ending arrives. For most of the binary's existence, changes occur gradually. But as the orbit tightens, Gravitational wave emission increases dramatically. Energy loss accelerates. Orbital speed rises. The black holes begin circling each other faster and faster. Eventually, the final phase begins. In the last minutes, the system behaves with astonishing violence. Objects heavier than stars whip around each other at significant fractions of light speed. Spacetime twists violently nearby. Gravitational waves surge outward with increasing intensity. And after billions of years of slow motion, the final merger happens in less time than it takes to boil a kettle. The contrast is almost comical. The universe spends ages preparing for events that conclude almost instantly. There is another subtle point here that often goes unnoticed. Black holes do not consciously find each other. No intention exists in the process. Gravity alone guides everything. Matter curves space-time. Objects follow those curves. Energy dissipates. Orbits evolve. The entire sequence emerges naturally from physical law, and yet from the human perspective, it feels oddly narrative. Two stars born together die together. Two black holes spiral inward across unimaginable ages before finally colliding in darkness. We instinctively interpret patterns as stories because our minds are built that way. Perhaps that is why astronomy feels so emotionally powerful sometimes. Even when the universe behaves mechanically, the outcomes often resemble myths or epics unfolding across cosmic scales. Ancient people looked upward and imagined gods fighting among the stars. Modern astrophysics describes gravitational collapse and relativistic spirals. Strangely, both approaches recognize something immense and dramatic overhead. Of course, not every black hole pair successfully merges. Some systems are disrupted before collision. Supernova kicks can fling black holes apart at enormous speeds. Nearby gravitational interactions may destabilize orbits. Dense clusters can eject black holes entirely. The cosmos is messy, but enough systems survive that mergers appear common throughout universal history. Every detection made by instruments like LIGO and Virgo confirms this further, and those detections themselves are fascinating because they reveal not just isolated events but populations. Some merging black holes are surprisingly massive. Some spins align unexpectedly. Some collisions occur farther away than anticipated. Each signal teaches us something about how black holes form, evolve, and eventually meet. Humanity is effectively learning the social behavior of invisible gravitational objects, which would sound completely absurd to almost anyone living a century ago. Yet, here we are. And perhaps the most humbling part is realizing how ordinary these mergers may actually be from the universe's perspective. To us, black hole collisions feel exotic and terrifying. To the cosmos, they may simply be part of routine structure formation. Galaxies merge, stars collapse, gravity gathers remnants together. Darkness combines with darkness. Reality ripples outward. The process repeats endlessly across space and time. Right now, somewhere beyond the stars visible tonight, two black holes are almost certainly orbiting each other in silence. Perhaps they have another billion years remaining, perhaps only 1,000. Perhaps their final collision already happened long ago, and the gravitational waves are still travelling toward us through the expanding universe. Because that is another strange feature of cosmic events. Even after they happen, the information takes time to arrive. The universe we observe is always slightly old. Light carries history. Gravitational waves carry history too. At first, almost nothing appears to happen. That may sound disappointing considering we're discussing black holes, but the universe often hides its most dramatic events behind astonishingly slow beginnings. Human beings tend to expect explosions, visible chaos, giant flashes of energy announcing that something important is underway. Black hole binaries rarely behave that way in the beginning. For most of their existence, they simply orbit. Two invisible objects moving around each other in darkness, steadily, patiently. And if you could somehow watch one of these systems from very far away during its early stages, You might not even realize you were observing something extraordinary at all. There may be no bright lights surrounding the pair, no dramatic jets, no obvious signs of violence, just motion. Two masses locked together by gravity, circling a shared center of balance through empty space. Yet underneath that calm movement, something irreversible is already unfolding. The orbit is shrinking. Very slowly at first, almost insultingly slowly by human standards, but continuously nonetheless. This gradual inward movement is one of the most beautiful predictions of Einstein's general relativity, because it reveals that gravity is not static. Orbiting objects do not merely move through space-time, they disturb it. Accelerating masses create ripples called gravitational waves, and those waves carry energy outward into the universe, which means every orbit costs something. The black holes lose a tiny amount of energy each time they circle, and because energy determines the structure of the orbit, the pair must move closer together. The process resembles a spiral staircase narrowing toward its center, or perhaps two skaters holding hands while slowly being pulled inward across ice. Except these skaters weigh more than stars, distort time itself, and can spend billions of years completing the performance. That duration is difficult to truly imagine. Human beings are not naturally equipped for billion-year thinking. Our minds evolved around days, seasons, lifetimes. Even history feels distant after only a few thousand years. Once numbers stretch into millions or billions, the brain starts treating them less like real durations and more like abstract scenery. So it helps to shrink the scale mentally. Imagine compressing Earth's entire history into a single calendar year. On that scale, dinosaurs disappear only a few days before midnight on December 31st. Human civilization occupies mere seconds. A black hole binary may spend the equivalent of months on that cosmic calendar, quietly spiraling inward before the final merger happens in an instant near the end. Gravity is remarkably patient, and strangely enough, the slower the process feels, the more inevitable it becomes. Each orbit changes the next orbit. Every revolution removes energy. The separation decreases little by little. Now, in ordinary life, when two objects spiral inward, friction is usually involved somehow. Air resistance, heat, contact with matter. But black holes often orbit in near vacuum, where there is essentially no traditional friction at all. Instead, the energy loss happens through gravitational radiation itself. This idea once seemed almost absurd. Einstein himself was uncertain whether gravitational waves represented physical reality or merely mathematical artifacts inside his equations. The waves were predicted by general relativity in 1916, but for decades many scientists debated whether they actually existed in any meaningful sense. Part of the problem was their weakness. Gravity is extraordinarily feeble compared to other forces. A tiny refrigerator magnet can overcome the gravitational pull of the entire Earth on a paperclip. Generating detectable gravitational waves requires immense masses moving at incredible speeds. Black hole binaries provide exactly those conditions, and even then the effect remains astonishingly subtle over long periods. In the 1970s, astronomers Russell Hulse and Joseph Taylor discovered a binary pulsar system that provided indirect proof of gravitational waves. The two neutron stars orbited each other while slowly losing energy, exactly as Einstein's equations predicted. The orbit shrank over time, not dramatically, not in ways visible moment to moment, but measurably. The system behaved precisely like two objects radiating gravitational energy into space. It was one of the earliest strong confirmations that the universe really does ripple, and black holes behave similarly, only on even more extreme scales. Imagine two black holes separated by millions of kilometers. They may orbit each other once every few days or weeks initially. The gravitational wave energy emitted at that stage is relatively modest compared to the final merger. Still, the loss continues relentlessly. Thousands of years pass, then millions. The orbit tightens gradually. And here the process becomes oddly self-reinforcing. As the black holes move closer together, orbital speed increases. Faster acceleration generates stronger gravitational waves. Stronger waves carry away more energy. More energy loss shrinks the orbit further, which increases speed again. The spiral slowly accelerates itself. At first the changes remain subtle, but eventually the system crosses into a regime where the inward spiral becomes noticeably faster. A useful comparison might be water circling a drain. Far from the centre, movement seems gentle and broad. Closer inward, everything speeds up dramatically. Black hole binaries behave somewhat similarly, except instead of water following fluid dynamics, space-time itself is doing the twisting. And because black holes affect time as well as space, the system becomes increasingly strange the closer the pair approaches merger. Near massive objects, time passes differently relative to distant observers. This phenomenon, gravitational time dilation, means clocks near strong gravity tick more slowly compared to clocks farther away. Now place two black holes near each other. Each object exists inside the distorted spacetime of the other. The geometry becomes extraordinarily complicated. Modern physicists require enormous computer simulations to model these systems accurately, because Einstein's equations become almost impossibly difficult to solve analytically during the latent spiral phase. Entire supercomputers may spend weeks calculating mere seconds of black hole motion. That alone says something profound about the complexity of gravity. People sometimes assume gravity is the simplest force because it feels familiar. Things fall downward. Apples drop from trees. Very approachable. But under extreme conditions, gravity becomes deeply wild. Space bends. Time stretches. Energy escapes as ripples in reality itself. And somewhere inside all this complexity, two invisible objects continue their long inward dance. There is also something emotionally peculiar about the silence of the process. Black hole mergers do not happen with sound in the conventional sense because sound requires matter like air or water to travel through. Space is mostly vacuum. Even the final collision unfolds silently across the cosmos. Yet if gravitational waves are converted into audio frequencies, they produce brief rising chirps, strange little upward sweeps in pitch corresponding to the accelerating orbit. The first detected merger sounded oddly tiny considering its scale. A short chirp. That was all. Yet hidden inside that sound was the final moment of two black holes colliding more than 1 billion light-years away. There is something wonderfully humbling about that contrast. The largest events in the universe do not necessarily announce themselves loudly. Sometimes reality whispers. During the inspiral phase, another interesting thing can happen depending on the environment surrounding the black holes. If gas and dust remain nearby, the binary may interact with surrounding matter. Accretion disks can form. Magnetic fields may develop. Friction within gas clouds can alter the orbit further, sometimes accelerating in spiral. In supermassive black hole binaries especially, the surrounding galactic environment matters enormously. Entire stars may wander near the pair and receive gravitational slingshot kicks outward. Gas clouds can become heated and disrupted. The binary gradually transfers energy into the surrounding galaxy while shrinking inward itself. In a sense, the black holes reshape their environment long before collision. And yet, despite all this activity, the final stages still occupy only a tiny fraction of the system's total lifespan. That imbalance feels almost unfair. Billions of years preparing, seconds concluding. The universe appears strangely comfortable with a symmetry like that. Stars spend most of their lives quietly fusing hydrogen before dying rapidly. Galaxies drift slowly for eons before sudden mergers. Civilizations may rise gradually and collapse quickly. Nature often accumulates tension patiently before releasing it all at once. Black hole binaries embody that principle perfectly. Another fascinating aspect involves orbital eccentricity. Not all black hole pairs orbit in neat circles. Some follow elongated elliptical paths. In those systems, the black holes swing closer together at one point in the orbit and farther apart at another. Each close approach emits stronger gravitational radiation. Over time, gravitational wave emission tends to circularize the orbit gradually, smoothing the path into something more regular. But the details reveal important clues about how the binary formed. Circular orbits often suggest long isolated evolution from stellar binaries. More eccentric systems may indicate chaotic formation in dense clusters, where gravitational interactions constantly reshuffle objects. Essentially, the shape of the orbit preserves fragments of the system's history. Astronomers are learning to read those clues the way geologists read rock layers, or archaeologists interpret ruins. Except instead of pottery fragments, they analyze distortions in spacetime itself, which still feels slightly unbelievable when stated plainly. There is also the issue of spin alignment. Black holes can rotate extremely rapidly. When two spinning black holes orbit each other, their spins interact with the orbit in complicated ways. Sometimes the orbital plane wobbles and precesses like a spinning top losing balance. This creates subtle signatures inside the gravitational wave signal. Again, scientists can detect some of this. Human beings have built instruments capable of measuring the dance orientation of invisible black holes billions of light years away. Honestly, if you explained modern astrophysics to someone from the medieval period, they might assume you were describing wizardry. And perhaps the most extraordinary thing about these systems is how isolated they often are from ordinary cosmic life. Imagine a black hole binary quietly and spiraling somewhere in a distant galaxy. Nearby stars continue shining. Planets may orbit peacefully around suns in the same galaxy. Perhaps life evolves somewhere nearby entirely unaware of the colossal merger slowly approaching. Because the timescales are so vast, the in-spiral phase becomes almost part of the background structure of the universe itself. Civilizations could theoretically emerge and vanish many times before the final collision even begins. There is something strangely comforting about that perspective too. Human urgency feels smaller against cosmic patience. Our species measures time obsessively. Minutes matter to us. Deadlines matter. Delays frustrate us. Entire emotional states can hinge on waiting a few hours too long for news or sleep or change. Black holes would find this behavior baffling. Gravity does not hurry. It simply continues. Orbit after orbit, century after century, age after age. And while the in-spiral progresses, the emitted gravitational waves spread outward continuously across the universe. These waves are not particles moving through space like bullets or tiny objects. They are distortions of distance itself. As a wave passes, space stretches slightly in one direction, while compressing in another. The effect is unbelievably tiny by the time it reaches Earth, but still measurable with sufficiently precise instruments. That precision borders on miraculous. The LIGO detectors, for example, measure changes thousands of times smaller than a proton across 4-kilometer laser arms. To do this, scientists must account for earthquakes, thermal noise, passing trucks, quantum fluctuations, even waves crashing on distant coastlines. Humanity essentially built giant machines capable of noticing when the universe breathes, and those breaths come from systems like in-spiraling black holes. All the while, the binary itself continues tightening. The orbital period decreases, the speed rises, the gravitational waves grow stronger. What once required days now takes hours, then minutes. Eventually, the black holes orbit each other several times every second. By that stage, the system becomes one of the most violent environments in existence. But oddly enough, violence is still not the right emotional word for it. Violence suggests chaos. The in-spiral remains astonishingly orderly. Einstein's equations describe the motion with exquisite precision. Even under such extreme conditions, gravity follows mathematical structure faithfully. The black holes do not crash randomly. They spiral inward according to geometry itself. And perhaps that is the strangest thing about all. Beneath the terrifying scale and overwhelming energy lies elegance. The universe bends, the orbit tightens, reality ripples outward. Human beings are used to thinking of space as empty. That sounds simple enough at first. Space is where things are. Stars exist inside it. Planets move through it. Galaxies drift across it. We imagine space as a kind of cosmic container, vast and mostly quiet, where matter floats around like objects inside an ocean. But near two orbiting black holes, that comfortable idea starts breaking apart. Because space is not passive. Neither is time. Einstein changed that forever. Before relativity, scientists often treated space and time as separate backgrounds. Space was the stage. Time was the ticking clock above it. Matter moved around while both remained steady and unaffected. General relativity destroyed that picture completely. Instead, space and time form a single connected structure called spacetime, and this structure bends, stretches, twists, and changes shape depending on mass and energy. Which means near a binary black hole system, reality itself becomes deeply distorted. Not metaphorically, literally. If you could somehow travel safely near two orbiting black holes, you would not simply see strange objects moving through ordinary space. You would exist inside a region where the geometry of existence has become warped beyond normal intuition. Distances behave differently. Time behaves differently. Light behaves differently. Even the concept of straight movement begins losing its familiar meaning. And perhaps the strangest part is that none of this would necessarily feel dramatic at first. Relativity often behaves quietly. You would not see glowing cracks in reality or giant spirals opening in the sky. Space-time curvature is not visible the way clouds or mountains are visible. Instead, you would notice its effects indirectly through motion, gravity, and light itself. Imagine placing a marble on a perfectly flat floor. It rolls in a straight line. Now imagine the floor bending and curving unpredictably beneath it. The marble's path changes, not because some invisible force grabbed it, but because the surface itself changed shape. Gravity works similarly in relativity. Objects follow the geometry of curved space-time, and near binary black holes the geometry becomes extraordinarily complicated because two immense gravitational wells constantly move around one another. This creates one of the most dynamic environments in the universe. A single black hole already distorts nearby reality profoundly. Space compresses toward it. Time slows near it. Light bends around it, but add a second black hole orbiting nearby, and the situation becomes vastly more chaotic. Now the distortions move. Imagine two whirlpools spinning close together in water. The currents overlap. The surface becomes unstable and complicated. Patterns interfere and shift constantly. Binary black holes create something similar in space-time itself. Every orbit changes the structure around them, and because the black holes accelerate while orbiting, the distortions cannot remain static. The geometry continuously rearranges itself. This constant shifting is what produces gravitational waves. Space-time ripples outward from the moving system. That phrase can feel abstract until you slow down and really think about what it means. The universe is not merely containing motion. The universe itself is moving. Distances stretch and compress rhythmically as waves pass through space. If a sufficiently strong gravitational wave moved through your body, the distances between atoms would change slightly for an instant. Your shape would distort microscopically, then return to normal. Fortunately, by the time gravitational waves reach Earth from distant mergers, the distortions are tiny beyond comprehension. Near the black holes themselves, however, the warping becomes extreme, and there is another peculiar consequence. The closer you move toward strong gravity, the slower time passes relative to distant observers. This is not illusion. It is not psychological. It is a measurable feature of reality. A clock near massive gravity genuinely runs differently. Now place two black holes near each other, each affecting the structure of time around the other. The result becomes astonishingly strange. Suppose you hovered near the binary system at a safe distance, while another observer remained far away from the black holes. You might experience a few hours while days or weeks pass elsewhere, depending on the strength of the gravitational field and your position. Near the final stages of inspiral, the effects become even more dramatic. Time itself stretches unevenly around the pair, and because the black holes orbit rapidly, regions of distorted time rotate as well. Reality near the system becomes dynamic and unstable in ways human intuition simply never evolved to handle. People often ask what it would look like visually near black holes, and the answer is deeply unsettling. Light bends enormously in strong gravity. Stars behind the black holes would appear distorted into arcs and rings through gravitational lensing. Entire sections of the sky could duplicate, twist, or smear visually as light followed curved paths through warped space-time. Around a single black hole, light can orbit temporarily in structures called photon spheres. Near binaries, these effects become vastly more complex. The sky itself would seem fluid, not because the stars move quickly, but because the geometry carrying their light changes constantly. And since each black hole bends light from the other as well, the visual structure near the system would become almost impossible to interpret intuitively. Computer simulations of binary black hole environments often look surreal for exactly this reason. The distortions are not artistic exaggerations. They emerge naturally from relativity. Reality near strong gravity genuinely stops behaving in familiar ways. Even directions become problematic. Far from gravity, forward feels obvious. Space behaves predictably. But near binary black holes, curvature alters path so strongly that movement itself becomes counterintuitive. A beam of light fired straight may curve dramatically. An orbit that seems stable may suddenly destabilize. Space becomes less like empty emptiness and more like shifting terrain. Another fascinating aspect involves frame dragging. Rotating black holes twist nearby space-time around themselves. This means the black holes do not merely sit inside curvature. They actively drag reality along with their spin. Now imagine two spinning black holes orbiting each other. The surrounding space-time becomes a tangled rotating structure of extraordinary complexity. Nearby matter may experience precession, wobbling orbital behavior caused by interacting gravitational effects. Accretion disks can twist and warp. Magnetic fields become tangled. Even the orientation of nearby orbits may gradually shift over time, and all this occurs before the merger itself even begins. The binary system effectively churns the local geometry of the universe. There is something strangely beautiful about that idea. Gravity often gets described as pulling, but relativity paints a more elegant picture. Matter tells space-time how to curve, and curved space-time tells matter how to move. Near binary black holes, that conversation becomes almost violent in intensity. The geometry never settles. Every orbit rearranges the structure again. And as the inspiral accelerates, the distortions grow stronger. At large separations, the black holes may orbit once every days or weeks. The surrounding space-time still changes dynamically, but relatively gradually. As the pair spirals inward, orbital periods shrink dramatically. Hours become minutes. Minutes become seconds. Near the final stages, the black holes can orbit each other dozens or even hundreds of times per second depending on mass. At that point, space-time around the system becomes extraordinarily turbulent. Not turbulent like air during a storm, because there is no medium flowing around in the ordinary sense. Instead, the geometry itself oscillates violently. Gravitational waves pour outward. The curvature fluctuates rapidly. The black holes essentially whip reality around themselves, and yet from far away, the system may still appear deceptively small and quiet. That contrast feels important somehow. The The universe does not always advertise its extremity clearly. Some of the most violent events in existence occur silently in darkness. No fire, no sound, just geometry becoming unstable. Another curious consequence involves causality itself. In ordinary life, cause and effect feel straightforward because time flows uniformly enough for human experience. Near strong gravitational distortions, however, the sequencing of events can become complicated from different perspectives. Observers in different positions may disagree about timing. Signals travel along curved paths. Light delays become significant. Reality becomes more observer-dependent than our instincts prefer. This does not mean causality breaks completely. Physics still behaves consistently, but the simplicity of everyday experience disappears. Near binary black holes, reality feels less absolute and more relational. That idea disturbed many scientists deeply when relativity first emerged. People are comfortable imagining different viewpoints on objects. One person sees a mountain from the east, another from the west. But relativity extends this flexibility into space and time themselves. Different observers genuinely measure durations differently. Different paths through gravity produce different experiences of time. Binary black holes push those effects toward extremes. And then there is the issue of tidal forces. Gravity weakens with distance. Near a compact object like a black hole, that change can become severe across relatively short distances. If your feet experience stronger gravity than your head, the difference stretches you. Near stellar mass black holes, tidal forces close to the event horizon can become catastrophic. Matter gets pulled into long thin streams through a process humorously nicknamed spaghettification, which is one of those rare scientific terms that somehow manages to sound both terrifying and slightly adorable. Near supermassive black holes, interestingly, tidal forces at the event horizon may actually be gentler, because the horizon lies farther from the central singularity. You could theoretically cross the event horizon of a very large black hole without immediate destruction, though escaping afterward would still be somewhat challenging. And by somewhat challenging, physics means impossible. Near binary systems, tidal environments become even more complicated because two gravitational sources constantly shift relative to one another. Matter caught nearby may become stretched, compressed, heated, and accelerated unpredictably. Gas clouds can collide and heat enormously. Magnetic fields twist into intricate structures. Entire stars wandering too close may be torn apart gravitationally. The region becomes one of the harshest environments in the cosmos. Yet despite all this complexity, Einstein's equations continue describing the system with extraordinary accuracy. That remains one of the most astonishing achievements in science. General relativity was developed in 1915 using mathematics, thought experiments, and physical reasoning. Einstein had no black hole images, no gravitational wave detectors, no supercomputers, and still, more than a century later, his theory continues successfully predicting the behavior of some of the universe's most extreme systems. Not perfectly, perhaps. Quantum gravity still remains unresolved. But the predictive success is extraordinary nonetheless. It means that when we simulate binary black hole spacetime today, we're not merely inventing artistic approximations. We're calculating genuine structures reality appears to follow, and those structures reveal something profound. Space and time are not fixed backgrounds. They're active participants in cosmic events. Near binary black holes, this becomes impossible to ignore. The universe flexes, curves, oscillates. Reality itself becomes dynamic. For most of human history, the universe appeared silent. Not quiet in the emotional sense. People certainly imagined the heavens filled with meaning, movement, and divine voices. Ancient cultures built myths around constellations. Philosophers described cosmic harmony. Poets spoke of the music of the spheres. But scientifically speaking, space seemed mute. We looked outward using light alone. Everything humanity learned about the cosmos came through: electromagnetic radiation, visible light from stars, radio waves from galaxies, X-rays from violent cosmic events, infrared heat drifting through dust clouds. Astronomy was fundamentally visual even when the wavelengths themselves were invisible to human eyes. Then Einstein quietly predicted something extraordinary. According to general relativity, accelerating masses should create ripples in spacetime itself, not particles moving through space, not ordinary vibrations inside matter, but distortions of reality spreading outward at the speed of light. Gravitational waves. At first, the idea sounded almost absurdly delicate. Spacetime itself rippling? Reality stretching and compressing? Even Einstein sometimes doubted whether these waves represented physical phenomena or merely strange artifacts inside the mathematics of relativity. The problem was gravity's weakness. Compared to other forces, gravity is astonishingly feeble. A tiny magnet can overpower Earth's entire gravitational pull on a paperclip. To generate noticeable gravitational waves, the universe requires immense masses accelerating violently. Ordinary human activity produces effects so tiny they are meaningless. A person waving their arms technically creates gravitational waves, but the distortion is unimaginably small. The universe does not particularly care about our aerobics routines. Black hole mergers, however, are another matter entirely. When two black holes orbit each other, they churn space-time itself. Their motion generates waves spreading outward across the cosmos like expanding ripples on a pond. Except ponds are simple. Water waves move through a medium. Gravitational waves are stranger because they are oscillations of distance itself. That idea deserves slowing down. Imagine 2 points floating in empty space. As a gravitational wave passes, the distance between those points changes slightly. One direction stretches while another compresses. Then the pattern reverses rhythmically as the wave moves onward. Space itself flexes, not metaphorically, physically. The effect is unbelievably tiny by the time such waves cross Earth. Detecting them became one of the greatest technical challenges humans ever attempted. And yet black hole mergers produce gravitational waves powerful enough to shake the structure of the universe across billions of light years. There is something deeply unsettling about that. Two invisible objects collide somewhere unimaginably far away, and reality itself carries the news outward through space-time. No medium required, no sound, just geometry changing shape. The first direct detection happened on September 14th, 2015. At the LIGO observatories in the United States, instruments measured a tiny distortion passing through Earth. The signal lasted only a fraction of a second, a brief upward sweep in frequency and intensity, a chirp, that was all. Yet hidden inside that tiny signal was one of the most violent events ever observed. Two black holes, about 30 times the Sun's mass each, had collided roughly 1.3 billion light-years away. During the final fraction of a second, they orbited each other at extraordinary speeds before merging into a single larger black hole. And in that brief instant, roughly 3 solar masses were converted directly into gravitational wave energy. Think carefully about that. 3 suns, not destroyed through ordinary explosion, but transformed into ripples in space-time itself. For a tiny fraction of a second, the collision produced more power than all the stars in the observable universe combined. Then the waves spread outward through darkness for over 1 billion years before brushing gently across Earth, and human beings detected them. That achievement remains astonishing. The distortions measured by LIGO were smaller than 1,000th the width of a proton. To observe them, scientists built gigantic laser interferometers with 4-kilometer arms capable of measuring absurdly tiny changes in length. The precision required borders on the unreasonable. Passing trucks create noise, earthquakes create noise, ocean waves crashing on distant coastlines create noise, thermal vibrations inside atoms create noise, quantum fluctuations create noise, even random microscopic disturbances inside the mirrors themselves become important. Humanity, essentially constructed giant machines sensitive enough to notice when the fabric of reality twitches. And those twitches came from black holes. There is something emotionally moving about that accomplishment. A species living briefly on a small rocky planet figured out how to detect invisible ripples produced by colliding objects across cosmic distances. Sometimes science feels less like collecting facts and more like teaching the universe new ways to become observable. Before gravitational wave astronomy, black hole mergers were largely theoretical events inferred indirectly. After 2015, they became measurable realities. Suddenly the universe gained a new sense. People often compare this transition to hearing. Imagine living your entire life able only to see. You understand motion visually. You observe storms and trees and oceans silently. Then one day hearing appears. Thunder exists now. Music exists. Voices exist. The world becomes richer and stranger overnight. Gravitational wave astronomy did something similar for humanity's understanding of the cosmos. We no longer merely observe light. We observe motion inside space-time itself. And black holes, once almost impossible to study directly, suddenly became accessible in entirely new ways. The shape of a gravitational wave signal contains enormous amounts of information. As two black holes orbit, the frequency and amplitude of emitted waves increase gradually. Faster orbits create higher frequency waves. Stronger acceleration produces larger distortions. Scientists can read these patterns almost like fingerprints. The signal reveals masses, spin rates, orbital behavior, distance, even hints about how the binary formed, all extracted from tiny ripples crossing Earth. It still sounds slightly impossible when described plainly. Another remarkable thing is how clean the signals often are. Light-based astronomy frequently struggles with dust, gas, magnetic fields, and complicated environmental interactions. Gravitational waves pass through matter almost unaffected. They travel across the universe carrying direct information about violent gravitational events. In a sense, they are pure geometry. The waves do not care about darkness. They do not scatter easily. They simply propagate outward, carrying the history of moving mass, which means black hole mergers occurring in completely invisible regions can still become detectable. The universe no longer needs to glow for us to study it. And perhaps the strangest aspect is that these waves constantly pass through us unnoticed. Right now, Earth exists inside a sea of gravitational disturbances from countless cosmic processes. Most are far too weak to detect individually. But reality itself is never perfectly still. Space-time flexes continuously. The planet stretches and compresses microscopically as waves pass. Human beings remain blissfully unaware because the effects are so tiny on ordinary scales. Our bodies evolved for forests and weather and social interaction, not for sensing geometric distortions in the fabric of the cosmos. Still, part of me finds it oddly comforting that the universe is quietly rippling all the time. Like an ocean too vast for direct perception, the detected signals themselves also possess an eerie beauty. When converted into audio frequencies, black hole mergers produce short rising tones because the orbit accelerates toward collision. The chirp increases in pitch and intensity rapidly before stopping abruptly at merger. People often expect something grander sounding considering the scale involved, but the universe rarely behaves according to cinematic expectations. The first black hole merger sounded tiny, a quick chirp. Yet behind that chirp lay impossible violence. There is a lesson hidden there somewhere about scale and perception. Not everything enormous feels enormous from far away. Another fascinating detail involves the speed of gravitational waves. General relativity predicts they travel at light speed, and observations confirm this extremely accurately. When neutron stars collided in 2017, scientists detected both gravitational waves and electromagnetic radiation from the same event. The signals arrived nearly simultaneously, after travelling over 100 million light-years. That agreement provided another extraordinary confirmation of relativity. Einstein continues winning arguments from beyond the grave with impressive consistency. The neutron-star merger also introduced something new. Unlike black hole mergers, neutron-star collisions produce visible light and matter ejecta alongside gravitational waves. Astronomers suddenly had both hearing and sight for the same event. The future of astronomy increasingly involves combining multiple messengers: light, gravitational waves, neutrinos, cosmic rays. The universe communicates through many channels. Humanity is only beginning to listen properly. Meanwhile, black hole mergers remain uniquely elegant sources of gravitational waves because the systems are relatively simple. No solid surfaces, no complicated nuclear reactions, just gravity dominating everything. In some sense, black hole binaries represent pure relativistic laboratories, and their signals allow scientists to test general relativity under extreme conditions impossible to recreate on Earth. So far, Einstein's theory continues surviving every test remarkably well. But physicists remain hopeful that subtle deviations might eventually appear, revealing deeper physics beneath relativity itself. Perhaps quantum gravity effects, perhaps entirely new phenomena. Black holes sit dangerously close to the boundaries of current understanding, which makes every detected merger scientifically precious. And the detections keep coming. Since 2015, LIGO, Virgo and other observatories have observed dozens of black hole mergers. Some systems contain surprisingly massive black holes. Others show unusual spin alignments or unexpected properties. Each signal expands humanity's map of cosmic behaviour, and we are still at the beginning. Future detectors promise vastly greater sensitivity. The planned space-based observatory LISA will detect lower frequency gravitational waves from supermassive black hole binaries millions of years before merger. Pulsar timing arrays already hint at gravitational wave backgrounds produced by giant black hole populations across the universe. Eventually, humanity may map cosmic structure partly through gravitational wave astronomy. An entirely new view of reality is unfolding. Yet despite all the advanced mathematics and instrumentation involved, there remains something emotionally simple about gravitational waves too. They are movement-carrying memory. A collision happens, the universe shivers, the shiver travels outward. Eventually someone far away notices. That sequence feels strangely intimate for something occurring across billions of light years. And unlike light, gravitational waves cannot easily be blocked or hidden. They pass through matter almost freely. Entire galaxies offer little resistance. The waves from ancient mergers move through stars, planets, oceans and bodies alike. Reality remembers motion, even after the original event has vanished completely. The black holes merge. The old binary disappears, but the distortion continues spreading outward forever. There is something haunting about that permanence. A merger lasting less than a second may continue influencing the geometry of the universe indefinitely as waves propagate endlessly into expanding space. In a sense, black hole collisions never fully stop happening. Their consequences simply become thinner and weaker over time, and while gravitational wave detectors currently measure only the largest events, the universe likely contains countless smaller ripples from orbiting stars, collapsing systems, spinning neutron stars, and perhaps processes not yet discovered at all. The cosmos may be far more acoustically active than humans once imagined, not with sound exactly, but with rhythm, motion encoded into geometry. For billions of years the black holes have been patient. Orbit after orbit they spiraled inward through darkness so gradually that entire galaxies could evolve around them without noticing much had changed. Stars were born nearby, stars died nearby. Light crossed enormous distances while the binary quietly tightened itself through the steady loss of gravitational energy. And then, near the end, patience disappears. The final seconds arrive with astonishing speed. This contrast is one of the strangest things about black hole mergers. Almost the entire story unfolds slowly beyond comprehension, yet the climax happens in less time than it takes to read a sentence aloud. Gravity spends ages preparing the collision, then suddenly everything accelerates at once. By this stage, the black holes are no longer separated by millions of kilometers. The distance has collapsed dramatically. Their orbital speed rises to extraordinary levels, sometimes approaching a significant fraction of the speed of light itself. Objects heavier than stars begin whipping around each other dozens or even hundreds of times per second, depending on their masses. Try imagining that properly for a moment. Masses containing many suns orbiting each other faster than kitchen blender blades, and not through ordinary space either. They move inside violently curved spacetime where distances, time and light itself no longer behave normally. This is one of the most extreme environments in the universe. If you could observe the system safely from far away during these last moments, you would see nothing directly with your eyes because the black holes themselves emit no light. But the surrounding geometry of space-time would be undergoing catastrophic oscillations. Gravitational waves surge outward enormously now. The waves that spent billions of years whispering through the universe suddenly become roaring distortions by relativistic standards. Every orbit releases staggering amounts of energy, and each orbit happens faster than the last. The black holes are no longer gently spiraling inward. They are plunging. This stage is called the inspiral, but near the end the word starts sounding too calm for what is actually happening. The system becomes dynamically unstable. The distinction between separate orbits and final merger begins dissolving. Space-time itself churns around the pair, and yet what makes the situation so unsettling is the precision hidden underneath all the violence. Nothing random is happening. Einstein's equations still govern everything. The black holes follow exact relativistic paths determined by gravity and geometry. Even under these impossible conditions, the universe remains mathematically structured. The final seconds are not chaos. They are inevitability accelerating toward completion. Another remarkable thing is how rapidly the orbital frequency increases. Earlier in the binary's life, one orbit may have taken days or weeks. Near merger, orbital periods shrink to milliseconds. The gravitational wave signal rises in pitch continuously as the black holes accelerate. That famous chirp detected by LIGO is literally the sound of orbit itself speeding up. Faster, 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 then suddenly stopping. And inside those last moments, the energies involved become almost absurd. During the final fraction of a second, black hole binaries can outshine the entire visible universe in gravitational wave power, not in light, not in explosions, but in pure distortion of space-time. The collision releases more energy per second than trillions of stars combined. Human language struggles with scales like that. Numbers stop behaving emotionally after a certain point. The brain hears more energy than all stars combined, and quietly gives up trying to picture it accurately. Perhaps that is understandable. Reality near merging black holes no longer resembles ordinary experience in any meaningful way. Time itself behaves strangely there. Suppose you could somehow survive near the system during the final seconds, which unfortunately would require ignoring several important laws of biology and common sense. Your experience of time relative to distant observers would differ enormously because of the intense gravitational field. Outside observers might watch clocks near the merger running strangely slow. Signals become distorted. Light bends violently. Space compresses and stretches dynamically around the orbit. Even defining simple concepts like distance or simultaneous events becomes problematic. General relativity turns ordinary intuition into something fragile near strong gravity, and the black holes themselves continue rotating. Most black holes spin because the stars that formed them possessed angular momentum. During merger, those spins interact with the orbit in incredibly complicated ways. Sometimes the spins align neatly, sometimes they tilt, sometimes the entire orbital plane wobbles and precesses as if the system itself struggles to maintain orientation. Supercomputer simulations reveal astonishingly intricate motion during these final stages. The black holes can dance around each other with behaviours that look almost organic despite being entirely governed by physics. There is something eerie about that. Pure geometry can appear graceful. Another fascinating detail involves the event horizons themselves. As the black holes approach each other, their horizons begin distorting. They no longer remain simple, isolated spheres. Gravity stretches and deforms the surrounding structure of space-time. Eventually, the horizons start interacting directly, and this is where language becomes especially inadequate because black holes do not possess solid surfaces that physically crash together like planets or billiard balls. The merger is not an impact in the ordinary sense. Nothing hits in a familiar way. Instead, the geometry of the horizons themselves rearranges. Two regions of no escape gradually become one larger region. The event horizons fuse. Reality rewrites its own boundaries. And while all this happens, gravitational waves continue carrying information outward. The waves encode the exact motion of the black holes during the final plunge. Scientists reading those signals can reconstruct masses, spins, orbital geometry, and properties of the resulting merged black hole. Essentially, the universe broadcasts the merger through spacetime itself, and remarkably, we can decode the transmission. The final moments also represent one of the best laboratories for testing general relativity under extreme conditions. Earlier stages of inspiral occur in comparatively moderate gravitational regimes. Near merger, however, gravity becomes fully nonlinear and violently dynamic. This is where Einstein's theory faces some of its hardest tests. So far, it continues passing with extraordinary success. The detected signals match relativistic predictions astonishingly well, which honestly remains one of the greatest scientific triumphs of modern civilization. Human beings developed mathematical equations over a century ago, then later built instruments capable of confirming those equations using collisions between invisible objects billions of light years away. That sentence alone feels slightly unreal, yet the universe continues behaving accordingly. Near the final seconds, the orbital velocity becomes so high that relativistic effects dominate completely. The black holes may circle each other at over half the speed of light. Imagine something containing dozens of solar masses moving that fast. The kinetic energy becomes enormous. The gravitational wave emission becomes enormous. Everything about the system approaches extremity. And still, from far away, the merger remains visually dark. This is one reason black hole collisions feel emotionally strange compared to supernova or exploding stars. Human instincts associate violence with brightness and sound. We expect catastrophic events to announce themselves dramatically. Black holes reject that expectation. Their most violent moments happen in silence and darkness. Only space-time itself reveals what occurred. If surrounding matter exists nearby, things can become more visually active. Gas may heat, magnetic fields may twist. Radiation could emerge from interactions outside the horizons. Some models predict electromagnetic counterparts under specific conditions, but many black hole mergers occur almost invisibly except for gravitational waves. Two invisible objects meet, reality shakes, then darkness remains. There is something profoundly unsettling about that restraint. Another curious phenomenon during the final seconds is gravitational recoil. If the emitted gravitational waves carry momentum asymmetrically, the newly formed black hole can receive a kick. In some mergers, the recoil velocity becomes enormous, potentially thousands of kilometers per second. Imagine two black holes colliding so violently that the merged remnant gets launched across space. Entire supermassive black holes may sometimes be ejected from galactic centers through this process. The universe, once again, demonstrates a surprising talent for absurdity. And through it all, causality continues forward, relentlessly, There is no pause before merger, no hesitation. The orbit tightens until separate motion becomes impossible to sustain. The horizons approach, the waves intensify, the plunge accelerates, and then something remarkable happens. For a brief instant, the binary system stops existing. Not because the black holes disappear, but because the distinction between them vanishes completely. Two objects become one. That transition happens extraordinarily quickly. Milliseconds, perhaps. Less time than a blink. After billions of years orbiting each other through darkness, the black holes finally cross the point where individuality ends and merger begins. There is something oddly philosophical about that too. The universe often spends immense time building separate structures, only to combine them eventually into larger ones. Stars form galaxies. Galaxies merge into clusters. Black holes merge into larger black holes. Gravity gathers. That is what gravity does best. It reduces separation. And perhaps what makes the final seconds so mesmerizing scientifically is that they reveal reality operating near its deepest limits. Space and time become dynamic. Geometry becomes violent. Energy becomes nearly incomprehensible. And somewhere inside all this complexity, Einstein's equations continue describing events with astonishing precision. Yet physicists know something remains incomplete. Inside the newly forming horizon lurks the unresolved problem of singularities and quantum gravity. General relativity works beautifully outside the event horizon, but eventually the theory predicts infinities where understanding breaks down. The merger pushes nature toward those boundaries, which means every detected collision is not merely an astrophysical event, it is a message from the edge of current knowledge. The universe keeps showing us phenomena that modern physics can describe extremely well, while simultaneously hinting that something deeper still waits underneath. And perhaps that tension is part of what makes black holes so compelling. They are both understood and mysterious at the same time. We can calculate their mergers with extraordinary accuracy, yet we still do not fully know what happens inside them. The final seconds before impact embody that contradiction perfectly. The mathematics becomes exact. The physical meaning becomes strange. The black holes accelerate beyond ordinary imagination. Gravitational waves explode outward across the cosmos. Reality itself oscillates violently. Then comes the moment itself. After billions of years orbiting through darkness, after the long spiral inward and the final violent acceleration, the black holes finally cross the threshold where they can no longer remain separate objects, and strangely enough there is no impact in the ordinary sense. No collision like planets striking each other, no explosion like stars going supernova, no fiery detonation spreading across space. What happens instead is far stranger. The structure of space-time itself reorganizes. That is the closest ordinary language can probably get to describing it. Two event horizons become unstable as independent boundaries. Their gravitational fields overlap so completely that the geometry surrounding them can no longer support two separate regions of no escape. A new common horizon forms around both black holes together, and once that happens, the merger is effectively unstoppable. From the outside perspective, the two black holes have become one larger black hole. But the details hidden inside that sentence are astonishingly complicated. The first thing worth understanding is that event horizons are not physical surfaces. This point matters enormously, because people naturally imagine black holes as giant dark spheres crashing together like cosmic cannonballs. That is not what is happening. You cannot touch an event horizon the way you touch a wall or a table. The horizon is a boundary in space-time geometry. It marks the region beyond which all future paths lead inward. So during merger, there is no solid impact. Instead, the geometry defining escape itself changes shape. Imagine two whirlpools in water drifting closer and closer until the currents overlap completely and form one larger whirlpool. That comparison is imperfect, but emotionally closer to reality than the idea of objects smashing together. The black holes stop being distinct gravitational regions they fuse into a single gravitational structure, and during this process, spacetime becomes extraordinarily unstable. The final orbit collapses, the horizons distort violently, gravitational waves erupt outward with peak intensity. For a brief instant, the system becomes one of the most energetic places in the observable universe. Now, one of the strangest things about the merger is how quickly it happens. The binary may spend billions of years approaching this point, yet the actual transition from two black holes to one occurs in milliseconds for stellar mass systems. That imbalance feels almost surreal. Gravity works patiently for unimaginable spans of time, then resolves everything nearly instantly. And while the merger unfolds, the emitted gravitational waves reach maximum strength. This is the loudest moment in gravitational wave terms. Not loud with sound, of course. Space remains silent in the ordinary sense. But the distortions of reality itself become immense. During this brief interval, the black holes are moving so fast and warping space-time so severely that enormous amounts of mass energy convert directly into gravitational radiation. The system literally loses part of its mass. This often surprises people. The final black hole weighs less than the combined masses of the original pair, because some energy escaped outward through gravitational waves. According to Einstein's famous equation, mass and energy are equivalent. So when gravitational waves carry energy away, the resulting black hole ends up lighter than simple addition would predict. For example, in the first detected merger, two black holes weighing about 36 and 29 solar masses combined into a remnant weighing roughly 62 suns. 3 solar masses vanished into gravitational wave energy, not destroyed, transformed. Reality itself carried the energy away as ripples in geometry. And perhaps the most unsettling thing is that this process remains almost entirely invisible. If no surrounding matter exists nearby, the merger may produce no light at all. Two invisible objects combine silently in darkness, while the fabric of the universe shakes. That sentence still feels strange even after years of scientific confirmation. Human instincts expect violence to be visible. Black holes refuse that expectation. Another remarkable aspect of the merger is how smooth the final result becomes afterward. At the instant of fusion, the newly formed black hole is not stable. The geometry around it vibrates violently. The merged horizon oscillates and distorts before gradually settling down into equilibrium. Physicists call this stage the ring down. It is one of the most poetic scientific terms ever invented, although the underlying physics is terrifyingly extreme. The name comes from the way a struck bell vibrates after being hit. The black hole behaves somewhat similarly. After merger, it rings through gravitational waves while shedding irregularities and asymmetries. Except instead of metal vibrating in air, it is space-time itself oscillating around an event horizon. Eventually the oscillations fade, the black hole stabilizes, and what remains is astonishingly simple. According to general relativity, black holes are described almost entirely by just 3 properties: mass, spin, and electric charge. That is all. No visible scars remain from the merger, no permanent wrinkles, no memory of the 2 separate objects beyond those conserved quantities. This idea led physicist John Wheeler to summarize black holes with the famous phrase, "Black holes have no hair," which sounds less like astrophysics and more like oddly specific shampoo advice, but the meaning is profound. Black holes erase complexity. 2 enormously complicated histories merge together, and the final object becomes mathematically simple. The universe performs one of the most violent events imaginable and leaves behind elegance. There is something deeply eerie about that. Another fascinating detail involves the shape of the newly formed horizon during merger. Computer simulations reveal that horizons can stretch, twist, and form astonishing geometries before settling down. During the actual fusion, the combined event horizon emerges dynamically, reshaping itself continuously. This process cannot be observed directly from inside because no information escapes outward from beyond the horizon. But the external gravitational wave signal carries indirect information about the dynamics. Again, human beings somehow learn to reconstruct invisible geometry from ripples crossing the universe. That still feels miraculous. And while the merger itself appears smooth from relativity's perspective, physicists suspect something deeper and stranger may occur inside. General relativity predicts singularities within black holes, regions where density becomes effectively infinite, and known physics breaks down. During merger, those singular regions would presumably combine as well. But this is where current understanding becomes incomplete. Quantum mechanics and relativity refuse to cooperate fully under such conditions. We do not yet possess a successful theory of quantum gravity, capable of describing what truly happens at the deepest interior levels of a black hole merger. This means that while we understand the external gravitational behavior remarkably well, the ultimate internal reality remains mysterious. In some sense, the merger occurs right at the edge of modern knowledge. The equations work beautifully outside the horizon. Inside, the fog returns. And perhaps that mystery contributes to why black holes fascinate people so deeply. They represent both triumph and limitation simultaneously. We can detect them, measure them, simulate them, even hear their mergers through gravitational waves. Yet they still conceal fundamental aspects of reality from us. The universe allows partial understanding but withholds complete access. Another curious effect during merger is recoil. If the gravitational wave emission becomes asymmetric enough, the newly formed black hole can be kicked violently through space. In some simulations and observations, recoil velocities reach thousands of kilometers per second. Imagine something heavier than millions of suns being launched across a galaxy, because space-time waves carried momentum unevenly. Entire supermassive black holes may occasionally get ejected from galactic centers this way. The cosmos truly has no obligation to behave modestly. And through all this violence, causality continues smoothly. The merger does not tear open reality, or create cosmic cracks despite what certain science fiction films might suggest. Space-time becomes extreme, yes, but it remains governed by physical law. No magical portals appear. No universe-ending shockwave spreads outward, destroying galaxies. In fact, unless you were extremely close, you might never know the merger happened except through gravitational wave measurements. The energy release is enormous, but gravity interacts weakly with matter over large distances. That is why the waves can cross the cosmos almost undisturbed. There is something paradoxical about that too. The most energetic events in existence can remain almost completely hidden from ordinary observation. And meanwhile, the newly formed black hole settles down. Its final spin depends on the orbital momentum and original spins of the merging pair. Some remnants rotate extraordinarily rapidly, others more moderately. The merged object now contains the combined history of both original black holes, encoded only through mass and angular momentum. Everything else vanishes behind the horizon. The separate identities disappear completely. Gravity simplifies the universe aggressively. Another interesting point is that the merger technically changes the surrounding structure of space-time forever. Gravitational waves continue propagating outward indefinitely. The geometry of distant regions receives the information billions of years later. Even after the local system stabilizes, the ripple effects continue crossing the universe. In a sense, the merger never fully stops happening. Its consequences simply spread thinner across larger distances over time. And perhaps the strangest emotional aspect of black hole mergers is how impersonal they are. Human beings naturally attach meaning to collisions. We think of conflict, destruction, endings. But black holes do not care. Gravity simply follows geometry. The merger is not tragic, not malicious, not violent in the emotional sense. It is merely what happens when curved spacetime evolves according to physical law. and yet the scale feels overwhelming anyway. Two regions where escape is impossible orbit each other for ages, then combine into one larger region where escape is impossible. Reality folds inward on itself. The universe trembles, darkness grows larger. That sequence carries an almost mythological weight despite being entirely scientific. Perhaps because black holes sit so close to the boundaries of imagination. They feel less like ordinary astrophysical objects and more like places where the cosmos experiments with its own rules. When the merger is over, the universe becomes quiet again, almost immediately. That may be the strangest part of all. After the violent spiraling motion, after the final impossible orbit and the eruption of gravitational waves, after reality itself twists hard enough to shake the cosmos across billions of light years, silence returns with almost unsettling speed. No fire remains. No expanding cloud necessarily glows through space. No cosmic scar stretches visibly across the galaxy. Instead, at the center of everything, there is simply a new black hole. Larger, heavier, spinning rapidly, and extraordinarily calm compared to the chaos that created it. In many ways, the birth of the merged black hole feels less like an explosion and more like a settling. Gravity has spent billions of years pulling two objects inward until separate existence became impossible. Now that process is complete. The system has found a new equilibrium. The universe relaxes again. Except the object left behind is one of the most extreme things nature can produce. A merged black hole carries the combined mass and angular momentum of the original pair, minus the energy lost through gravitational waves. If two stellar black holes merge, the remnant may contain dozens or hundreds of solar masses. If supermassive black holes merge, the resulting object may outweigh entire galaxies' worth of stars combined. And yet, despite that unimaginable density, the final black hole becomes surprisingly simple. This simplicity is one of the weirdest features of black holes. Ordinary objects preserve visible complexity. Mountains remain rough. Stars possess magnetic fields, chemical layers, storms, and surface activity. Planets contain continents, oceans, atmospheres, and geological histories. Black holes erase almost everything. Once the merger settles, the remnant is described mainly by mass, spin, and electric charge. In astrophysical environments, charge usually becomes negligible, because opposite charges neutralize quickly. So most real black holes reduce essentially to two defining features. Mass, rotation, that is all. The final object contains no visible memory of the two original black holes, no grooves, no cracks, no lingering evidence of the collision beyond the values encoded into its overall structure. Gravity behaves like a ruthless editor. Complexity goes in, simplicity comes out. This led physicists to formulate the no-hair theorem, the idea that black holes shed all unnecessary information about the matter and events that formed them. The phrase still sounds slightly ridiculous considering the seriousness of the subject, but the principle is profound. Black holes are astonishingly efficient at hiding history. Imagine taking two enormously complicated systems, each born from massive stars with unique properties and long evolutionary paths, then merging them in one of the most energetic events in the universe, only for the result to settle into something mathematically elegant and almost featureless. Nature often behaves this way under gravity. Stars form from chaotic gas clouds, yet become nearly perfect spheres. Galaxies organize into graceful structures from turbulent beginnings. Black holes perhaps represent the most extreme version of this tendency towards simplification. Another fascinating aspect of the remnant black hole is its spin. When two orbiting black holes merge, enormous angular momentum is involved. Unless the spins and orbital motions cancel perfectly, which would be extremely unlikely, the final object rotates rapidly, very rapidly. Some merged black holes spin near the maximum rates allowed by relativity. And rotating black holes are deeply strange things. A spinning black hole, drags nearby spacetime along with it through frame dragging. The faster it rotates, the stronger the effect becomes. Around such an object exists a region called the ergosphere, where remaining stationary relative to distant space becomes impossible. Reality itself gets pulled into rotation. The newly formed black hole may continue influencing nearby matter dramatically after merger. Gas clouds orbiting nearby can become heated. Magnetic fields may twist violently. Jets may emerge from regions surrounding the horizon. In supermassive black hole systems, the aftermath of mergers may shape entire galaxies. That idea deserves slowing down a little because the scale involved becomes difficult to absorb. At the centre of most large galaxies lies a supermassive black hole. The one in the Milky Way, Sagittarius A star, contains about 4 million times the Sun's mass. Some galaxies contain black holes billions of times heavier than the Sun. When galaxies merge, their central black holes eventually merge too. The resulting object may influence star formation across enormous distances through gravitational effects and energetic outflows. Entire galactic structures can evolve partly under the influence of these giant dark remnants. So the birth of a larger black hole is not merely the ending of one story. It often becomes the beginning of another. Gravity gathers more matter, more stars drift nearby, more objects orbit. Eventually perhaps another merger happens again. The universe builds hierarchically this way. Small structures combine into larger ones repeatedly across cosmic history. And black holes may grow through generations of mergers over billions of years. This possibility becomes especially important because astronomers have detected black holes heavier than expected from ordinary stellar collapse alone. Some observed merger remnants appear to inhabit mass ranges once thought difficult to produce directly from dying stars, which suggests some black holes are descendants of earlier mergers. A black hole born from collision may later collide again, and later, again. Darkness inheriting darkness. The process feels almost evolutionary. Another strange consequence of merger birth involves recoil velocity. A symmetric gravitational wave emission can launch the newly formed black hole through space at tremendous speeds. Sometimes the kick remains modest. Other times it becomes extreme, thousands of kilometers per second, enough to eject the remnant entirely from its surrounding star cluster, or even from the center of a galaxy. Imagine an object heavier than millions of suns being hurled through intergalactic space because gravity radiated unevenly for a fraction of a second. The cosmos consistently refuses to behave modestly. If such a recoil occurs in a galactic center, the consequences could become significant. The displaced black hole may drag stars along gravitationally. Accretion behavior changes. Galactic dynamics shift over long timescales. Entire stellar environments respond to the birth and motion of the remnant, and still, the black hole itself remains dark. That contrast never stops feeling unsettling. The largest concentrations of gravity in existence remain visually hidden unless surrounding matter reveals them indirectly. Even after a spectacular merger, the remnant may appear almost invisible against the darkness of space. No glowing trophy marks the event permanently, just altered gravity. Another important point is that the merged black hole does not instantly become perfectly stable. After the horizons fuse, the remnant undergoes ring-down oscillations. Space-time around the black hole vibrates briefly while irregularities radiate away as gravitational waves. This stage resembles a struck bell gradually settling into silence. Except instead of metal vibrating through air, it is the geometry of reality oscillating around an event horizon. The frequencies of these oscillations depend directly on the black hole's properties. Scientists can analyze them to measure mass and spin with remarkable precision. Essentially, the black hole announces its final characteristics through the way space-time vibrates around it. There is something hauntingly elegant about that. Even silence contains information. And then eventually the ringing fades, the geometry smooths out, the remnant stabilizes into a Kerr black hole, The relativistic solution describing rotating black holes, at that point the merger truly ends, or at least locally, because the gravitational waves continue travelling forever outward across expanding space. Billions of years later, distant observers may still detect the signal. The birth cry of the new black hole keeps propagating through the universe, long after the original environment becomes quiet again. Reality remembers motion. That idea keeps returning throughout gravitational physics. The universe preserves traces of dynamic events through geometry itself. And perhaps one of the most emotionally strange aspects of black hole birth is how ordinary the remnant eventually becomes from the outside perspective. After all the violence and impossible energy release, the final black hole simply joins the cosmic population of other black holes. It sits, it rotates, it bends nearby space-time. Perhaps matter falls inward occasionally, perhaps stars orbit it quietly. The extraordinary event gradually becomes another stable feature of the universe. Nature has a remarkable ability to normalize extremity over time. Even the most violent processes eventually settle into structure. There is also something deeply philosophical about the way black holes grow. Most objects in life become more fragile as they accumulate history. Wear increases. Complexity builds. Systems degrade. Black holes behave differently. Growth often makes them more dominant, more stable, more influential. They gain mass through merger and accretion, while simplifying internally from the outside perspective. Gravity rewards accumulation, and over cosmic timescales, this accumulation may become enormous. Some supermassive black holes likely grew partly through repeated mergers over billions of years, while galaxies assembled around them. The early universe contained smaller structures that gradually combined into larger ones. Black holes followed the same trend. The universe appears surprisingly comfortable building giant invisible engines at galactic centres, and yet despite all this power, black holes remain oddly passive in a sense. They do not chase matter, they do not hunger consciously. Gravity simply shapes motion around them. The remnant black hole born from merger is not an aggressive predator suddenly unleashed upon the galaxy. It merely becomes another deep curvature in space-time, another place where escape proves impossible past a certain boundary. The drama belongs mostly to the geometry, and perhaps what makes the birth of a larger black hole feel so emotionally powerful is the contrast between permanence and transformation. Two separate objects cease existing forever. A new object emerges. The old identities vanish completely behind the horizon. Yet mass and angular momentum persist in altered form. Nothing is truly lost. Nothing remains entirely the same. The universe rearranges itself continuously this way. Stars become remnants. Galaxies merge. Matter changes state. Energy changes form. Black holes combine into larger black holes. Reality seems deeply committed to transformation across every scale, and somewhere far away tonight, another remnant black hole has probably just been born. Perhaps the merger happened millions of years ago, and the gravitational waves are still crossing the universe toward us now. Perhaps two giant black holes recently settled into silence at the centre of some distant galaxy, while stars continued orbiting nearby completely unaware. The cosmos does not pause after such events, it simply continues, orbit after orbit, galaxy after galaxy, merger after merger. And while the newly formed black hole stabilizes in darkness, another question naturally begins emerging from the silence left behind. What would happen to anything unfortunate enough to exist nearby when such a collision occurs? The honest answer is probably not, at least not if near means truly near. Black hole mergers are among the most extreme gravitational events in existence, and the environment surrounding the final collision becomes so violent that ordinary matter stands very little chance of remaining intact. The energies involved are overwhelming. Space-time itself distorts dynamically. Tidal forces become catastrophic close to the horizons. And yet, like most things involving black holes, the details turn out to be stranger and more complicated than simple destruction. Because black holes do not kill things the way explosions kill things. There is no expanding wall of fire racing outward through space, no blast wave behaving like a cosmic bomb in vacuum. In fact, one of the unsettling things about black hole mergers is how localized the most dangerous effects often are. Gravity weakens rapidly with distance, so survival depends enormously on where you are. Very far away, you might notice almost nothing at all. Closer in, reality becomes increasingly hostile, and extremely close to the merger, the environment stops behaving in ways biology could possibly tolerate. To understand why, we need to begin with tidal forces, because those are often the first truly lethal aspect of black holes. Gravity always changes with distance. If you move farther from Earth, gravity weakens slightly. Normally, this difference is small enough that human beings never notice it. Your feet experience slightly more gravity than your head, but the variation is tiny. Near black holes, however, gravity changes incredibly rapidly across short distances. This creates tidal stretching. If one part of your body experiences significantly stronger gravity than another part, the difference pulls you apart. Near stellar mass black holes, this effect becomes devastatingly strong close to the event horizon. A falling object can be stretched into long, thin streams through a process scientists rather cheerfully nicknamed spaghettification, which sounds like something involving a kitchen accident rather than relativistic death. But the underlying physics is brutal. Now place two black holes together in their final inspiral. The tidal environment becomes enormously more complicated. Gravity shifts continuously as the pair orbits at relativistic speeds. The curvature of space-time changes dynamically. Regions of strong stretching and compression move around violently. Anything orbiting too close would experience extraordinary gravitational stress. Stars wandering near the binary may be torn apart entirely. Gas clouds become heated to extreme temperatures. Orbits destabilize. Matter gets accelerated unpredictably. The final seconds before merger are especially dangerous because the black holes orbit each other so rapidly that the surrounding geometry effectively churns, and still, oddly enough, there is no conventional explosion. This remains deeply counterintuitive. Human beings associate catastrophic events with expanding destruction. Supernovae blast matter outward violently. Nuclear explosions generate shock waves. Volcanoes erupt. Storms spread. Black hole mergers behave differently. Most of the released energy escapes as gravitational waves, and gravitational waves interact only weakly with matter. That means a black hole merger occurring far enough away may pass through surrounding regions with surprisingly limited direct physical destruction. You would not want to be nearby, certainly, but nearby, in astrophysical terms, matters enormously. For example, Earth itself is not remotely threatened by ordinary black hole mergers elsewhere in the galaxy or universe. Gravitational waves crossing Earth produce distortions smaller than atoms. LIGO measures them only through absurdly sensitive instrumentation. The universe can shake space-time tremendously, while barely disturbing matter at large distances. This creates a strange paradox. The merger is simultaneously one of the most energetic events in existence, and one of the least physically disruptive across great distances. Reality itself absorbs most of the violence. Another fascinating question involves planets orbiting near supermassive black hole binaries. Could such planets exist? Surprisingly, perhaps yes under certain conditions. Supermassive black holes possess event horizons vastly larger than stellar black holes. Tidal forces at equivalent distances may actually be gentler, because the curvature gradient changes differently over scale. Far enough from the central pair, stable orbits might theoretically persist for some time. Of course, stable becomes a flexible word near merging supermassive black holes. The environment would still be deeply unpleasant by ordinary standards. Accretion disks surrounding active binaries can produce enormous radiation fields. X-rays and gamma rays may flood nearby space. Magnetic interactions become violent. Gas clouds heat dramatically. Any nearby planetary system would likely face severe radiation exposure long before the actual merger. Atmospheres could strip away. Surfaces sterilize. Oceans evaporate. Black holes themselves are dark, but the matter around them often becomes lethally bright. And if the merger occurs inside an active galactic nucleus, conditions may resemble the inside of a cosmic furnace. Still, farther outward, survival becomes increasingly plausible. The universe operates heavily on scale. A black hole merger a few astronomical units away would be catastrophic. A merger thousands of light years distant might become scientifically interesting rather than dangerous. Distance changes everything. Another important factor involves recoil kicks. Asymmetric gravitational wave emission can launch the newly formed black hole through space at enormous velocities. Nearby stars and matter may experience sudden changes in gravitational structure as the central object moves. Imagine orbiting a massive object that suddenly receives a kick of thousands of kilometers per second. Orbital stability becomes questionable rather quickly. Stars may be flung into new trajectories. Planetary systems destabilize. Entire central regions of galaxies could reorganize over long timescales. So even after the merger ends, nearby environments may continue evolving dramatically. And then there is the issue of accretion. Matter surrounding the binary does not simply ignore the merger. Gas clouds can collide and compress violently. Magnetic fields twist. Shock heating may occur in surrounding material. Some models predict bursts of electromagnetic radiation after certain mergers due to disturbed accretion disks. This means nearby matter could experience indirect effects more dangerous than the gravitational waves themselves. Not because spacetime ripples tear matter apart directly at large distances, but because the merger rearranges the environment around it. The aftermath can become chaotic. Another deeply unsettling possibility involves stars caught near the system during inspiral. A star wandering too close to the binary may experience complex gravitational interactions. Sometimes the star gets ejected at enormous speed through gravitational slingshot effects. Other times, tidal disruption occurs. In a tidal disruption event, the star gets stretched and shredded by gravity. Stellar material forms streams spiraling around the black holes while heating intensely. The process can release enormous radiation. Essentially, the star becomes cosmic soup. Black holes possess a remarkable talent for turning ordinary matter into extremely energetic disasters, and yet the black holes themselves remain perfectly silent throughout all this. That contrast keeps returning. The violence happens around the darkness, not inside it. Another strange consideration involves what an observer would actually experience visually near merger. Assuming impossible protection from tidal forces and radiation, the view would likely become deeply disorienting. Light bends dramatically around strong gravity. The sky would distort into arcs and warped structures through gravitational lensing. Nearby stars might appear duplicated or stretched. Time itself behaves differently depending on position. Signals arriving from distant space would become distorted. Reality near the merger would feel less like ordinary space and more like unstable geometry. And perhaps the most terrifying aspect is how little warning ordinary matter receives. A star drifting near the system does not experience fear or anticipation. Gravity simply reshapes its orbit until survival becomes impossible. The universe behaves impersonally. Black hole mergers are not aggressive in any emotional sense. They do not hunt. They do not target. They merely obey geometry with overwhelming consistency. That impersonality somehow makes the whole process feel even stranger. There is no malice in the destruction, just inevitability. Another fascinating question scientists explore is whether black hole mergers could influence life on galactic scales. Generally speaking, most mergers occur too far, away to matter significantly to biological systems elsewhere. Galaxies are enormous. Even powerful events weaken dramatically with distance. However, Extremely energetic environments near active supermassive black hole binaries might affect star formation, radiation conditions, and galactic structure over long periods. Indirectly, black holes may shape where life becomes possible simply by influencing how galaxies evolve. That idea carries a certain cosmic irony. The darkest objects in the universe may help determine where stars and planets eventually form. Destruction and creation remain strangely intertwined in astrophysics. And perhaps the most emotionally interesting answer to the survival question is this. The farther you move from the merger, the more ordinary the universe remains. At sufficient distance, life continues normally. Stars shine peacefully. Planets orbit quietly. Civilizations could theoretically exist within the same galaxy entirely unaware that two black holes just merged somewhere far away. Meanwhile, gravitational waves from the collision spread outward invisibly through everything. Reality flexes gently, then settles again. The universe does not announce its most extreme events dramatically to everyone. Often the cosmos remains calm except in very localized regions. This becomes easier to appreciate when remembering how huge galaxies truly are. Even the Milky Way spans over 100,000 light years. Most stars remain separated by enormous distances. Space is astonishingly empty. That emptiness protects things. Even near violent astrophysical processes, most of the universe remains untouched, and perhaps that is comforting in its own way. Black hole mergers represent some of the harshest environments known to science, yet existence continues elsewhere almost undisturbed. The cosmos contains room simultaneously for unimaginable violence and remarkable tranquility. Somewhere tonight, stars are probably being torn apart near binary black holes. Somewhere else, planets drift quietly beneath calm skies. The universe allows both realities at once. Human beings are deeply attached to the idea that time flows normally. Seconds pass, clocks tick. Morning becomes afternoon and eventually night. Even when life feels chaotic, time itself seems dependable. We expect it to move forward steadily for everyone everywhere. Two people standing in different cities may disagree about politics or weather, or whether pineapple belongs on pizza, but they generally agree on how clocks behave. Black holes destroy that comfort. Near strong gravity, time stops behaving universally. And during a black hole merger, time enters one of the strangest environments in the known universe. This is not science fiction. It is one of the most firmly tested predictions of general relativity. Gravity affects time, literally. A clock near strong gravity runs more slowly compared to a clock farther away. This effect is called gravitational time dilation, and it has been measured repeatedly with extraordinary precision. Even on Earth, time behaves differently at different altitudes. A clock on a mountain ticks slightly faster than a clock at sea level because it sits farther from Earth's gravitational field. The effect is tiny here, of course. Human beings never notice it directly, but satellites absolutely do. GPS systems must constantly correct for relativistic time differences, or navigation would fail quickly. So relativity is not abstract philosophy. Your phone already depends on it. Now imagine replacing Earth with two merging black holes. The gravitational field becomes unimaginably stronger, and more importantly, it becomes dynamic. That word matters enormously. A single stationary black hole already distorts time profoundly. Two orbiting black holes create moving regions of extreme time distortion, interacting continuously with one another. Reality itself becomes unstable in temporal terms. Suppose you hovered near a black hole binary at a theoretically safe distance, while another observer remained far away in deep space. Your experiences of time would diverge dramatically. Minutes for you might correspond to hours or days elsewhere, depending on proximity and orbital conditions, and as the merger approaches, the distortions intensify rapidly. The closer the black holes spiral together, the stronger the surrounding curvature of spacetime becomes. Time near the system stretches more severely relative to distant observers. Yet here is where relativity becomes emotionally strange. Locally, nothing feels wrong. This is one of the hardest aspects of time dilation to grasp intuitively. If you were near the black holes, your own heartbeat would feel normal. Your thoughts would proceed normally. A nearby clock would tick normally from your perspective. You would never feel time slowing. Instead, the difference only becomes apparent when comparing experiences with observers in different gravitational environments. Relativity does not make time feel slow. It changes how much time actually passes between events. And during a black hole merger, those differences can become extreme. Another unsettling aspect is that there is no universal now in relativity. Human intuition desperately wants one. We naturally imagine the universe sharing a single present moment, some cosmic clock synchronizing existence everywhere simultaneously. Relativity says no. Time depends on motion and gravity. Different observers measure durations differently. Different observers disagree about simultaneity itself. Near black hole mergers, this becomes impossible to ignore because the geometry of space-time changes violently and continuously. The very structure defining temporal relationships becomes dynamic, and because the black holes orbit rapidly during the final stages, regions of slowed time rotate through space along with them. This creates a situation almost impossible to picture properly with ordinary intuition. Imagine invisible whirlpools not only bending space but dragging different rates of time around themselves. Reality near the merger becomes temporally uneven. Another curious consequence involves observation itself. Suppose you watched an object falling toward one of the merging black holes from far away. Due to gravitational time dilation, the object would appear to slow down as it approached the horizon. Light emitted from it becomes increasingly redshifted and delayed. To distant observers, the object seems almost frozen near the horizon. Yet from the falling object's own perspective, time proceeds normally. It crosses inward. This disagreement between perspectives is not illusion. It is built into the structure of space-time. Near binary mergers, the situation becomes even more complicated because the horizons themselves move and distort dynamically. The geometry changes while the observations occur. Signals bend. Light paths curve. Time stretches differently depending on position. Reality stops behaving like a universal stage and starts behaving more like a network of interconnected perspectives. And perhaps nowhere does this become more emotionally unsettling than during the final moments before merger. The black holes orbit each other at relativistic speeds. Their gravitational fields overlap intensely. The emitted gravitational waves themselves carry information outward through distorted space-time. Everything about the system becomes extreme. Yet inside all this violence, time never breaks. That is important. Relativity produces bizarre effects, but it remains internally consistent. Cause and effect continue functioning. Observers may disagree about durations or simultaneity, but physical laws remain coherent. The universe does not descend into temporal chaos. Instead, time becomes relational, flexible, dependent on gravity and motion. And this flexibility leads naturally to one of the most famous questions about black holes. What happens to time at the event horizon? The answer depends entirely on perspective. From far away, objects approaching the horizon appear increasingly slowed. Signals become weaker and redder. The crossing itself seems delayed indefinitely. From the falling object's viewpoint, however, crossing occurs within finite time. This duality makes black holes deeply uncomfortable for human intuition because both descriptions are valid simultaneously within relativity. There is no single preferred perspective. Now place two event horizons together during merger. The complexity becomes extraordinary. The horizons distort and fuse dynamically, while time itself remains uneven across the surrounding geometry. Supercomputer simulations help physicists model these conditions, but emotionally understanding them remains difficult because ordinary life never exposes us to flexible time. Human experience evolved in weak gravity. Relativity hides from us most of the time. Black holes force it into the open. Another fascinating detail is that gravitational waves themselves carry timing information. The famous chirp detected by LIGO rises in frequency because the orbit accelerates. The increasing pitch literally encodes the changing temporal structure of the system. Scientists can reconstruct how fast the black holes orbited during their final moments by analysing the signal. In a sense, humanity learned to hear relativistic time speeding up toward merger. That still feels almost unbelievable, and while all this happens externally, there remains the deeper unresolved mystery inside black holes themselves. General relativity predicts singularities where known physics breaks down. Near those regions, ordinary concepts of time may cease functioning meaningfully altogether. Some solutions to Einstein's equations suggest bizarre possibilities involving closed time-like curves or distorted causal structure under extreme conditions. Quantum gravity likely changes the story dramatically, but no complete theory currently exists, which means black hole mergers sit dangerously close to the edge of current understanding about time itself. We know relativity works extraordinarily well outside horizons. Inside, certainty fades, and perhaps that uncertainty explains why black holes occupy such a powerful place in human imagination. They challenge our deepest assumptions, not just about matter or gravity, but about time itself. Human identity depends heavily on temporal structure. We remember the past, we anticipate the future, we experience existence sequentially. Black holes remind us that this experience may be far more local and conditional than we instinctively believe. Another strange emotional consequence emerges from considering how differently observers experience durations near strong gravity. Imagine civilizations existing in different gravitational environments. Their clocks would genuinely disagree. Their histories would unfold at different rates relative to one another. Near black holes, these differences become enormous. Time stops being universal background and becomes part of the landscape itself. A mountain affects movement through space. A black hole affects movement through time, and during merger, those temporal distortions churn dynamically across the surrounding region. Reality becomes almost fluid. Another unsettling possibility involves what distant observers see after the merger. From far away, the newly formed black hole settles through ring-down oscillations. Gravitational waves fade, the system stabilizes, but due to relativity, signals emitted near the horizons remain increasingly delayed and redshifted. The boundaries of observation themselves become tangled with time dilation. Black holes do not simply hide space, they hide futures, and perhaps the most extraordinary thing about all this is how experimentally confirmed it already is. Relativity's predictions about time are not speculative philosophy anymore. Atomic clocks verify them. GPS systems require them. Gravitational wave detections confirm them under extreme conditions. The universe genuinely allows time to stretch and diverge depending on gravity. Black hole mergers merely push those effects toward their most violent known limits. And yet, for all the mathematical precision involved, the emotional experience of contemplating this remains deeply strange. Human beings live by clocks. We organize existence into minutes and years and lifetimes. Near merging black holes, those familiar structures lose their universality. Time becomes curved, flexible, local, almost geological in its dependence on gravity. The cosmos stops treating time as a single river and reveals it instead as something woven into the geometry of reality itself. And somewhere in the universe tonight, two black holes are probably merging while nearby clocks run differently, depending on where they orbit, how strongly gravity grips them, and how close they drift to the impossible darkness at the center of the collision. Meanwhile, far away from the merger, Other observers continue living through entirely different rates of time without ever noticing the difference. Long before humanity ever detected a black hole collision, scientists already suspected the universe might be trembling constantly in ways no human senses could perceive. Einstein predicted gravitational waves in 1916, only a few months after finishing general relativity. According to his equations, accelerating massive objects should disturb spacetime itself, sending ripples outward at light speed. The mathematics allowed it naturally. But there was a problem. The predicted waves were unbelievably weak. Not weak near black holes themselves, of course. There the distortions become enormous. But by the time such ripples crossed interstellar or intergalactic distances and finally reached Earth, they would shrink to almost nothing. A passing gravitational wave might change the length of a 4-kilometre object by less than the width of a proton. That scale is difficult to emotionally process. Imagine trying to measure a change smaller than an atomic nucleus across a distance longer than many cities. For decades, many physicists quietly assumed direct detection would remain impossible forever, not because the theory was necessarily wrong, but because the universe simply seemed too subtle. Human civilization builds bridges and rockets and radio telescopes. Measuring distortions smaller than subatomic particles caused by black holes billions of light years away sounded unreasonable, even by scientific standards. And yet humanity kept trying. There is something deeply characteristic about that. People often describe science as cold or detached, but many scientific projects are powered by a very emotional refusal to stop asking impossible questions. Gravitational wave astronomy existed for decades, partly because generations of scientists looked at absurd technical obstacles and responded with, perhaps anyway. Eventually that persistence created LIGO, the Laser Interferometer Gravitational Wave Observatory, which sounds wonderfully dramatic once you know what it actually does. LIGO is not a telescope in the ordinary sense. It does not look at stars or galaxies through lenses. It does not collect visible light. Instead, it listens to the structure of spacetime itself. The observatories sit in Louisiana and Washington state, separated by thousands of kilometers. Each facility contains an enormous L-shaped interferometer with 2 vacuum tunnels stretching 4 kilometers long. Inside those tunnels, lasers bounce back and forth between mirrors with astonishing precision. At first glance, the setup sounds almost strangely simple for one of humanity's greatest scientific instruments. Just lasers and mirrors. But the simplicity hides terrifying technical difficulty. The basic idea works like this. A laser beam splits into 2 identical beams travelling down perpendicular arms. The beams reflect repeatedly between mirrors and eventually recombine. Under perfectly stable conditions, the waves line up in predictable ways. But if a gravitational wave passes through Earth, space itself stretches slightly in one direction and compresses in another. The lengths of the arms change by microscopic amounts. That tiny distortion alters the laser interference pattern, and from those changes scientists can detect the passing wave, which means LIGO does not really measure objects. It measures geometry. The machine notices when reality changes shape. That remains one of the most astonishing sentences modern science allows us to say with complete seriousness. And to accomplish this, LIGO required solving problems so extreme they almost sound fictional. The mirrors must remain isolated from vibration with incredible precision. Passing trucks matter. Tiny earthquakes matter. Ocean waves hitting distant coastlines matter. Wind matters. Thermal expansion matters. Even quantum uncertainty itself becomes important. The mirrors are suspended through elaborate isolation systems designed to minimize disturbances. The vacuum inside the tunnels is among the most perfect ever created on Earth, because even stray air molecules could interfere with measurements. The instrument became less like a machine and more like an attempt to create silence inside reality itself. Human beings built enormous quiet rooms so they could hear the universe whisper, and after decades of development, upgrades, skepticism, failures, and engineering nightmares, the moment finally arrived. September 14th, 2015. A gravitational wave passed through Earth. The signal reached Louisiana first, then Washington about 7 milliseconds later. Inside the data appeared a tiny rising chirp, exactly matching predictions for two merging black holes. At first, many scientists reportedly assumed it might be a mistake. That reaction feels understandable. The signal was too clean, too perfect. The black holes involved weighed roughly 36 and 29 times the Sun's mass. They had spiraled together for ages before merging into a single larger black hole about 1.3 billion light-years away. The final collision released energy equivalent to roughly 3 suns converted directly into gravitational waves, and after travelling for over 1 billion years, the distortion finally crossed Earth. The measured change was unimaginably tiny, yet LIGO detected it. Human beings heard black holes collide. That sentence marked a turning point in scientific history. For the first time, humanity observed the universe through gravity directly rather than through light. A completely new form of astronomy was born overnight. Until that moment, black holes remained difficult to study because they emit no light themselves. Scientists inferred their existence indirectly through surrounding matter, orbital motion, or energetic accretion disks. Gravitational waves changed everything. Now invisible collisions could become observable. Darkness itself became measurable. There is something emotionally profound about that transition. Imagine living your entire life able only to see, then suddenly discovering hearing. Entire categories of reality would appear instantly. Thunder, birdsong, music, voices. The universe, after gravitational wave detection, became richer in a similar way. And remarkably, Einstein had predicted all this a century earlier with equations written on paper. No computers, no lasers, no interferometers, just mathematics and imagination. General relativity had already survived many experimental tests before LIGO, but detecting gravitational waves carried special emotional weight because it confirmed something almost poetic hidden inside the theory. Spacetime is not static. Reality can ripple. That realization changed astronomy permanently, and once the first detection succeeded, more followed. Black hole mergers began appearing repeatedly inside LIGO data. Some black holes were larger than expected. Some spins behaved strangely. Some collisions occurred at astonishing distances. Each signal carried information about invisible systems scattered across the cosmos. Humanity was suddenly conducting population studies of merging black holes, which still sounds faintly absurd in the best possible way. Another fascinating thing about LIGO is how collaborative the project became. Thousands of scientists across many countries contributed to the effort. Physicists, engineers, mathematicians, computer scientists, material specialists, laser experts. Detecting gravitational waves required combining enormous amounts of human knowledge into one coordinated attempt to notice distortions smaller than atoms. There is something strangely hopeful about that. Modern civilization often feels chaotic and fragmented, yet projects like LIGO reveal another side of humanity entirely. People working together patiently for decades to answer questions about the structure of reality itself. And all this effort focused on something no human being can perceive naturally. Our senses are wonderfully limited things. We evolved to notice movement in forests, recognize faces, hear nearby predators, smell food. Evolution had no reason to prepare us for black hole mergers, so humanity invented artificial senses. Telescopes extend vision, radio dishes extend hearing, particle detectors extend touch into microscopic worlds. LIGO extends perception into geometry itself. The machine effectively allows our species to feel distortions in space-time. That idea still feels slightly supernatural even though it is entirely real. Another remarkable detail involves the sound of the signal itself. Scientists converted the gravitational wave frequency into audio humans could hear. The famous chirp lasts only a fraction of a second. The pitch rises quickly before stopping abruptly. It sounds tiny, small, almost delicate. And hidden inside that little chirp lies the final orbit of two black holes, moving near light speed and releasing more power than all stars combined for a brief instant. The contrast between scale and perception becomes almost comical. Reality does not care what humans expect enormity to feel like. Sometimes the largest events whisper. LIGO also forced scientists to confront how much activity had been hidden from view all along. Black hole mergers were not rare theoretical curiosities happening once somewhere distant. They appeared common throughout cosmic history. The universe had likely been filled with gravitational wave events the entire time humans existed, without anyone noticing. Reality was louder than expected. We simply lacked the ears, and now those ears continue improving. New observatories join the network: Virgo in Europe, Kagra in Japan, future detectors planned for space itself. The next generation of instruments may detect supermassive black hole mergers, primordial gravitational waves from the early universe, perhaps even unknown phenomena no one has imagined yet. Humanity has only just opened this sensory channel. The cosmos still contains enormous amounts left to hear. And perhaps what makes the story of LIGO feel so beautiful is how improbable it all was. A species living briefly on a small planet around an ordinary star somehow learned enough mathematics to predict gravitational waves, enough engineering to build detectors, enough patience to isolate microscopic noise, and enough collaboration to interpret the resulting signals. All so we could hear two invisible objects collide after a journey lasting over 1 billion years. The universe trembled, Earth moved by less than a proton's width, and humanity noticed. Far beyond the scale of stars and planets, the universe organizes itself into structures so enormous that human intuition begins failing quietly in the background. Galaxies drift through darkness in clusters containing hundreds or even thousands of other galaxies. Immense filaments of matter stretch across cosmic distances, almost too large to visualize properly. Between those filaments lie gigantic voids where very little exists at all, and threaded throughout much of this structure are black holes. Not merely the stellar remnants formed from dying stars, but supermassive black holes containing millions or billions of times the Sun's mass. Nearly every large galaxy we observe appears to host one at its center, which naturally raises a fascinating possibility. If black hole mergers release such enormous energy and alter space-time so violently, could enough of these events eventually reshape galaxies themselves? Could they influence the architecture of the universe on truly cosmic scales? The answer, surprisingly, is yes. Not in the dramatic science fiction sense where black holes rip galaxies apart overnight or swallow the universe whole. Gravity usually works more patiently than that. But over millions and billions of years, black holes absolutely help shape the cosmos around them. And in some cases, they may influence the evolution of entire galaxies. This realization emerged gradually during the late 20th century as astronomers began studying galactic centers more carefully. At first, supermassive black holes seemed almost incidental, strange heavy objects hidden inside galaxies, but not necessarily important to their overall structure. That view changed dramatically. The more scientists observed galaxies, the clearer it became that central black holes and galaxies appear deeply connected. The mass of a supermassive black hole often correlates strongly with properties of the surrounding galaxy, particularly the central bulge of stars. This was unexpected. Why should a black hole occupying a relatively tiny region influence a galaxy tens or hundreds of thousands of light years wide? Something important was clearly happening, and black hole mergers turned out to be part of the story. Galaxies collide surprisingly often across cosmic history. Not in the violent, explosion-filled way movies portray collisions, but through slow gravitational interactions lasting hundreds of millions of years. Stars inside merging galaxies usually do not crash into each other directly because space is so empty. Instead, the galaxies gradually pass through and around one another while gravity rearranges their structures. Spiral arms distort, gas clouds compress, star formation surges, and eventually the galaxies combine into one larger system. Meanwhile, at the centres of both original galaxies, supermassive black holes continue existing. Gravity slowly drags them inward toward the newly forming galactic centre. Eventually the pair becomes a binary system. Then the long spiral begins again. Two supermassive black holes, orbiting through darkness while entire galaxies evolve around them. The scale of this process is difficult to overstate. These are not merely black holes heavier than stars. Some contain masses equivalent to billions of suns compressed into regions smaller than our solar system. When such objects merge, the released gravitational wave energy becomes almost incomprehensible, and yet the merger itself is only part of the influence. Long before collision occurs, the binary system reshapes its galactic environment continuously. Stars wandering too close may receive gravitational slingshot kicks and get ejected outward at enormous speeds. Gas clouds become disturbed and heated. Orbital structures shift gradually over time. The black holes effectively stir the galaxy from within. Another remarkable effect involves star formation. Supermassive black holes surrounded by actively accreting matter can generate enormous jets and radiation fields. As gas falls inward toward the black hole, magnetic fields and gravitational energy accelerate particles outward at nearly light speed. These jets can stretch thousands or even millions of light years into intergalactic space, and they matter tremendously. Gas is the raw material from which stars form. If black hole activity heats or expels gas from a galaxy, star formation may slow dramatically. In some galaxies, active black holes appear capable of regulating how quickly new stars emerge. This process is called feedback, and it may help explain why galaxies evolve the way they do. In other words, black holes are not passive decorations inside galaxies. They may act more like giant gravitational regulators influencing cosmic ecosystems over billions of years. That idea feels almost paradoxical, the darkest objects in existence helping determine where stars and planets eventually form, and mergers amplify these effects. When supermassive black holes spiral together, they disturb enormous amounts of surrounding matter. Gas clouds collide and compress. Radiation environments change. Magnetic fields twist violently. Some simulations suggest that mergers can trigger bursts of galactic activity lasting millions of years afterward. Entire regions of galaxies may reorganize gradually due to the aftermath. Another fascinating possibility involves gravitational recoil. When two black holes merge asymmetrically, gravitational waves can carry away momentum unevenly. The resulting black hole receives a kick. Sometimes that kick becomes astonishingly large, thousands of kilometers per second, enough to eject the supermassive black hole entirely from the galactic center. Imagine a black hole weighing millions or billions of suns being launched through space, because the geometry of emitted gravitational waves happen to favor one direction slightly more than another. The universe has a remarkable ability to behave both elegantly and absurdly at the same time. If a supermassive black hole gets displaced or ejected, the consequences for the host galaxy could become significant. Galactic cores may destabilize, star orbits may shift gradually, gas behavior changes, feedback processes alter. The long-term evolution of the galaxy itself diverges from what would otherwise have happened. So yes, black hole mergers can reshape galaxies. Not instantly, not violently in the cinematic sense, but persistently and profoundly across cosmic time. Another strange realization emerged once astronomers started mapping the early universe. Supermassive black holes appeared surprisingly early after the Big Bang. This created a puzzle. How did such enormous objects grow so quickly? Ordinary stellar collapse and slow accretion seemed insufficient in some cases. Mergers likely contributed significantly. Small black holes combined repeatedly over time while galaxies assembled hierarchically. The universe appears to build large structures by merging smaller ones across many scales. Stars form galaxies. Galaxies form clusters. Black holes form larger black holes. Gravity gathers matter relentlessly. And perhaps the most interesting part is that the universe seems deeply structured around this process. Cosmic evolution is not random scattering. Matter organizes itself through gravity into increasingly complex arrangements. Black hole mergers participate directly in that architecture. Another question naturally follows from all this. Could black hole collisions affect the universe itself on the very largest scales? Here the answer becomes more subtle. Individual mergers, even supermassive ones, do not threaten the overall structure of the observable universe. Space is simply too large. Galaxies remain enormously separated. Gravity weakens rapidly with distance. Black holes are not secretly consuming the cosmos. The universe is expanding overall, and on large scales that expansion dominates over localized gravitational attraction between distant structures. So black holes do not represent some inevitable universal ending, where everything collapses into darkness, at least according to current understanding. Still, black holes may play important roles in the long-term future of the cosmos. Over unimaginable spans of time, galaxies continue merging. Star formation gradually declines as available gas becomes depleted. Black holes grow through accretion and collision. The universe may eventually enter eras dominated more by remnants than by active stars. In some far future models, black holes become among the last major structures still dynamically evolving, and even they are not eternal. Thanks to Hawking radiation, black holes slowly evaporate through quantum effects. The process is fantastically slow for large black holes, vastly longer than the current age of the universe, but not infinite. A stellar mass black hole might survive around 10 to the power of 67 years. Supermassive black holes last incomprehensibly longer, yet, eventually, even they fade. That realization feels emotionally strange. Black holes often seem like permanent cosmic prisons, eternal places where matter disappears forever. But quantum mechanics suggest even darkness leaks slowly back into the universe. The cosmos refuses absolute permanence. Another fascinating possibility involves primordial gravitational waves. If the early universe experienced violent inflationary expansion shortly after the Big Bang, spacetime itself may have generated enormous background ripples still detectable today. Modern gravitational wave astronomy may eventually help study conditions from near the beginning of time itself, which means the same physics allowing us to hear black hole mergers could also reveal information about the birth of the universe. Gravity connects scales in remarkable ways. Tiny ripples from colliding black holes, gigantic ripples from cosmic inflation, all carried through space-time. There is something deeply beautiful about that continuity. Another important point is that black holes may influence dark matter distributions indirectly through their gravitational effects. Entire galactic halos respond to central mass structures over long periods. And although dark matter itself remains mysterious, its interaction with galactic evolution likely intertwines with black hole growth in ways scientists are still uncovering. The deeper astronomy looks, the harder it becomes to separate black holes from cosmic structure overall. They are woven into the universe more deeply than early scientists imagined, and still, despite all this influence, black holes remain curiously restrained. They do not dominate everything locally. They coexist inside larger structures. Galaxies are not giant feeding grounds spiraling helplessly inward. Most stars orbit peacefully at enormous distances from central black holes. The Milky Way's supermassive black hole, Sagittarius A star, influences nearby stellar orbits strongly, yet Earth remains safely distant. Our planet orbits the galaxy comfortably without any dramatic interaction. Again, scale changes everything. The universe allows terrifying processes and calm environments simultaneously. Another emotionally interesting aspect of galactic black hole mergers is how ordinary they may actually be cosmically speaking. To human beings, such events feel almost mythological. Entire galaxies merging while central black holes spiral together sounds like something from ancient epics. To the cosmos, it may simply represent routine structure formation. Gravity builds larger systems from smaller ones continuously. The process repeats across billions of years with quiet consistency. And perhaps what makes this realization so humbling is understanding how temporary current cosmic conditions may be. Right now, the universe still shines brightly with active stars and ongoing star formation. But cosmic history stretches vastly beyond human timescales. Galaxies continue evolving, black holes continue merging. The structure of the universe keeps changing slowly. Reality remains unfinished. And somewhere tonight, beyond the visible stars, giant black holes are almost certainly orbiting each other at the centers of merging galaxies, while gravitational waves spread outward across intergalactic darkness. Entire stellar civilizations could theoretically rise and vanish before those black holes finally collide. Gravity remains patient. It always has been. Yet eventually the orbit tightens. The merger comes. The galaxy changes. And afterward, the universe moves forward again, carrying the consequences into even larger scales of time and structure. After everything we have learned about black hole collisions, gravitational waves, warped time, and cosmic evolution, what does it actually mean for human beings to live inside a universe so restless and so constantly in motion? Tonight, we followed two black holes across billions of years, not with rockets or telescopes in the ordinary sense, but through ideas, through gravity, through tiny distortions in spacetime that somehow crossed impossible distances and reached a small planet filled with curious creatures who decided they wanted to understand what the universe was doing in the dark. And perhaps the strangest thing we discovered along the way is that black hole collisions are not really about destruction alone. At first glance, they certainly seem terrifying enough. Invisible objects heavier than stars spiraling together through warped space-time, while reality itself bends and trembles around them. Entire suns' worth of mass converted directly into gravitational waves. Time stretching strangely near event horizons. Galaxies slowly reorganizing around enormous gravitational engines hidden at their centers. None of that sounds particularly comforting. Yet the deeper we traveled into the story, the more the universe began feeling less violent and more restless. That may be the better word for it. Restless. Because black hole mergers are not interruptions in the cosmos. They are part of its ordinary behavior. Stars are born. Stars collapse. Gravity gathers the remnants together. Galaxies merge. Space-time ripples outward. Darkness combines with darkness. The process continues endlessly across scales too large for human intuition to fully absorb. And meanwhile, life goes on elsewhere. That contrast stayed quietly present throughout everything we explored tonight. Near the merger itself, gravity becomes overwhelming. Time stretches. Matter tears apart. Space-time oscillates violently. Yet farther away, stars continue shining peacefully. Planets orbit calmly. Entire civilizations could theoretically exist inside the same galaxy, completely unaware that two black holes just collided somewhere beyond the visible sky. The universe allows tranquility and extremity simultaneously. That feels important somehow. Human beings often imagine reality in dramatic categories: safe or dangerous, quiet or violent, stable or chaotic. The cosmos rarely respects those boundaries. Instead, everything overlaps. Galaxies drift gracefully while harboring monstrous gravitational objects at their centers. Black holes remain silent while releasing unimaginable energy through gravitational waves. Space appears empty while constantly flexing with distortions too subtle for human senses to notice naturally. Even time itself turns out to be less fixed than we once believed. And perhaps that is what makes astronomy emotionally powerful in a very particular way. The universe does not simply provide information, it changes perspective. Once you learn that black holes can merge in darkness while reality ripples outward for billions of years afterward, ordinary life starts feeling slightly different around the edges. A clock becomes stranger once you realize time itself bends. Silence becomes stranger once you realize the universe is constantly trembling with gravitational waves. Darkness becomes stranger once you understand how much activity hides inside it. Right now, as you listen to this, the cosmos is still moving. Somewhere beyond the stars overhead tonight, binary black holes are orbiting one another. Some remain millions of years away from merger. Others may already be deep inside their final in-spiral, whipping around each other at relativistic speeds while space-time twists violently nearby. Perhaps one pair collided long ago, and the gravitational waves are still crossing intergalactic darkness toward Earth right now. The universe is always slightly older than the light reaching us. We never see things exactly as they are, only as they were when their signals began travelling. That idea feels strangely gentle tonight. Everything arrives eventually, even ripples from black holes, and what humanity accomplished by detecting those ripples remains extraordinary no matter how calmly we describe it. A species living briefly on a small rocky planet learned enough mathematics to predict gravitational waves more than a century before the technology existed to measure them. Then generations of scientists and engineers built instruments sensitive enough to detect distortions smaller than atoms caused by collisions between invisible objects billions of light years away. Also, we could hear the universe in a completely new way. That achievement says something hopeful about curiosity itself. Human beings are fragile creatures in many respects. We tire easily. We worry constantly. We forget passwords with alarming consistency. Yet we also possess this remarkable tendency to keep asking questions long after the answers seem unreachable. What are stars made of? What happens inside black holes? Does time behave the same everywhere? Can space itself ripple? Again and again, humanity looked outward into darkness and decided not knowing was temporary. There is something deeply comforting in that persistence, and black holes, despite their frightening reputation, have become one of the clearest reminders that the universe is richer and stranger than our instincts first assume. They are not cosmic monsters waiting to consume reality. They are natural consequences of gravity, places where matter curves space-time so intensely that ordinary experience stops being reliable. The terror they inspire often comes less from danger, and more from humility. Black holes force us to confront scales and conditions completely outside human life. We evolved beneath weak gravity on a quiet planet orbiting an ordinary star. The cosmos, meanwhile, contains regions where time slows dramatically, where stars are torn apart, where galaxies collide over hundreds of millions of years, and where invisible objects merge while releasing enough energy to shake the universe itself. Reality is far larger than the environments that shaped our minds. Still, somehow, we are capable of understanding parts of it. Not perfectly, not completely, but genuinely. That alone feels miraculous enough for one evening. Another strange comfort hidden inside black hole mergers is how much patience the universe contains. Gravity rarely rushes. Two black holes may spend billions of years spiraling inward before finally colliding in less than a second. Galaxies drift gradually toward merger across spans longer than multicellular life has existed on Earth. Even light itself takes time to travel between stars. The cosmos unfolds slowly. Human life often feels hurried by comparison. Days become crowded with schedules and obligations and clocks demanding attention constantly. We measure existence in deadlines and alarms and calendars. Black holes would find such urgency deeply confusing. Gravity is perfectly comfortable waiting 1 billion years for an orbit to shrink. Perhaps there is something calming in remembering that scale occasionally. Not because human life becomes meaningless against cosmic time, but because the universe clearly does not experience reality through panic. Everything moves, everything changes, yet most of it happens patiently. And perhaps the most haunting realization from tonight's journey is that nothing in the universe truly stands still. Not galaxies, not stars, not space-time itself. Even the emptiness between galaxies expands continuously. Gravitational waves stretch and compress the cosmos endlessly. Black holes merge, matter falls inward. Time flows differently depending on gravity and motion. Reality is dynamic all the way down. The stable world human beings perceive is partly an illusion created by living at one particular scale under relatively gentle conditions. Beneath that calm surface, the universe is endlessly active. And yet, despite all this motion, the cosmos does not feel chaotic tonight. That may be because large-scale motion often contains structure rather than randomness. Black hole mergers follow geometry, galaxies evolve through gravity, space-time obeys physical law with astonishing consistency. The universe behaves strangely, certainly, but not carelessly. There is elegance underneath the extremity. Perhaps that is why people continue returning emotionally to astronomy again and again. It provides both humility and connection simultaneously. We are small compared to black holes and galaxies and cosmic timescales, yes, but we're also made from the same universe that creates them. The atoms in human bodies were forged inside stars. The gravity shaping galaxies also keeps your feet on the Earth tonight. The same physical laws governing black hole mergers govern the motion of rain, oceans, trees, and heartbeats. The scales differ enormously. The underlying reality does not. And somewhere inside all this motion, on one quiet world among countless others, human beings developed enough awareness to wonder what happens when two black holes collide. That curiosity matters. It always has. Because curiosity is partly how the universe becomes conscious of itself. A strange thought for the evening, perhaps, but a comforting one too. The cosmos spent billions of years creating stars, planets, chemistry, life, minds, mathematics, and eventually machines capable of listening to space-time. Black holes collided long before humans existed, but now there are creatures able to notice the ripples. Reality gained observers, and tonight, for a little while, you became one of them. So as the evening drifts onward, and the universe continues its endless motion overhead, perhaps let yourself rest inside that perspective for a moment. Galaxies are moving, space-time is flexing, black holes are merging somewhere beyond sight, gravitational waves are crossing the darkness right now, and here on Earth, under a quiet sky, you are alive during the brief era when humanity first learned how to hear the universe breathe. Sleep well,